we have our slope management roadmap. You can see that although the first roadmap was earlier on, 2009, however, this is some of the abstract, the roadmap from 2017 until recently 2023. You can see that we are effectively trying to promote some regulation, enhancing our system. Okay, the sentences is quite small actually. All right. Okay. This is the abstract for our National Slope Master Plan, or we call in Plan Induk Curun National. The first was in 2009 until 2023. However, we have the plan to extend it for another 15 years. So this plan actually serves a roadmap with 10 main components. So this is under preview of this our slope engineering branch department, and the objective is the plan should be in a dynamic or in a living document. It should be reviewed and revised throughout the years as a national social, regulatory, and technological changes. It will be designed and also should be a comprehensive and also some effective framework. I would like to mention the 10 main components of this national master plan. The first is to establish the policy and with the institutional framework. Of course, we have this hazard mapping and assessment. We're going to reduce the loss assessment. We are going to have this early warning system and the real time monitoring. We are establishing the information collection, either interpretation, dissemination, and achieving. Of course, we should have enhancing the public awareness and education. Training is a needs, while we need to reducing loss reduction measures, and also we're going to have more responsiveness in dealing during the emergency preparedness and recovery. Lastly, we're going to enhance the research and development. Throughout the years, 94% of the key areas have been achieved. So as we go from bottom one, the top one, this pelan bahaya dan risiko curun has been established, or in other words, it's a slope danger risk and the plan. While I've been mentioned about this hazard, sustainability, and also the risk map. So we have done actually, but throughout the years, this one will be progressively carried out. And then also we are establish also our guidelines for linear and area based. All right. So public awareness, the guidelines, and also we're going to have the emergency preparedness response plan. So this is the innovation that we done in our department, slope engineering department. We have real-time rain gauge monitoring throughout in Malaysia and Peninsula. Not only that, in the Sabah and Sarawak, we also have this robotic total station RTS and also global navigation system GNS. See, this is the picture of the sensor and meter we have installed. And then this is the innovation that we are going to continue, such as manual guidelines and some technical notes for the maintenance, bioengineering, especially in the public department. So this is the disaster preparedness that we are prepared for every year. As I mentioned before, we have two types of monsoon season. One is the monsoon Barat Daya, or we call it southwest monsoon. Now, another one is Monsoon Timor Laut. This is northwest monsoon. So together with the Slope Engineering Department and Road Maintenance Department, we are representing JKR to be part of the LEDMA Disaster Task Force. So throughout the years, we are ready for any disaster mitigation measures during this time. And then a study by the Department of Irrigation has shows that about 10.1% of the country is prone to be a flood area. And then of course, there will be about 5.6 million people will be affected, and the cost will be the recurring cost will be about 1 billion per year for repairing all this slope and also the some assets. Okay, in conclusion, we have 7 key strategies in the slope engineering department. The first one, we are aimed to have corrective and emergency for all federal or state roads and also government buildings. We are having a slope preventive work in throughout the entire road for the Peninsula or Sabah and Sarawak. We are establishing our forensic and design in our department also. And then we are promoting our public awareness education. We are enforcing our Plan Induk Curun Negara, as I mentioned before, the master plan for slope Malaysia. We are going to have more data for the hazard maps. And also, lastly, we also become the consultancy for the government for PV area. Okay. With that, I would like to thank you for listening my presentation. And I can see that my last slide showing our countries and Hong Kong. Should be in the green actually. Okay. So this is the my last slide. So with that, thank you so much. Right.
Thank you very much, Dr. Sukri. It really is a wonderful presentation, and it's great to learn about the master plan, the roadmap, and also the emergency preparedness measures being implemented in Malaysia. I'm sure many of these also resonates with what we are doing and what we are going to do in Hong Kong. And I believe that many participants would like to raise some questions or comments, but then we'll leave it to the discussion section at the end of today's event. So please do still feel free to type in your questions. We will discuss them later today. Okay, so with that, we're going to have our next speaker, who's going to be our representative from the Geotechnical Engineering Office of Hong Kong. So let me try to so let's try to bring up the biography of Engineer Roy Hong for the benefits of all the participants. Right, so Engineer Roy Hong is currently a Chief Geotechnical Engineer in the Geotechnical Engineering Office of the Civil Engineering and Development Departments of the Hong Kong government. So his work is to oversee Hong Kong's territory-wide landslide prevention and hazard mitigation projects. Roy has more than 20 years of experience in tunneling, cavern engineering, quarrying, rock processing, and slope stabilization, and he's currently also a fellow of the Hong Kong Institution of Engineers and the Institute of Materials, Minerals, and Mining. So without further ado, let me pass the mic to Roy. So Roy, are you here?
Yeah, thanks, Andy, for your kind introduction. So, see if
So you might want to
are you able to hear me?
Uh,
Are
hello,
you
Roy.
able to hear me? Hello.
Yeah, we can hear you now.
Okay. So, it's my turn. Okay, let me share my screen. Okay. Okay. Okay, so thanks, our Hong Kong GES President Andy for this kind introduction. Okay, actually, it's also my honor to give a speech here on Hong Kong's landslide risk management. Actually, having listened to Dr. Amol Shuki's keynote speech just before about his work in Malaysia, I just found that there are actually many similarities about the landslide risk management in Malaysia and Singapore. Okay, it's quite a coincidence that actually, it seems to me that we both are aligned on the way we are managing the risk, the landslide risk. So I believe that is very likely. Just to echo what Andy has said, there will be many collaboration opportunities between the two places in this aspect. So well, in light of this, so after the keynote speech from Dr. Amol Shakis, so now it's my turn to share our experience from Hong Kong perspective. Okay, actually, I will first give an overview about the landslide risk management in Hong Kong, and then I will talk about that. Now, actually, we are moving towards to doing that. We are moving towards in order to do it in a smart and sustainable manner. Okay, well, to start with, actually, just like Malaysia, okay, Hong Kong is also prone to the risk of landslide because all these factors are combined. What they are the hilly terrain with a highly weather geological profile, which is about the topographical setting and the ground condition. Also, it's about the heavy rain and the intensive urbanization for the cases in Hong Kong. Actually, this is a map showing what we have in terms of the topographical setting and our ground condition. Okay, over our territory of about 1,000 kilometers square, actually, our developing areas is confined to about 270 kilometers square. And most of the ground mass actually is sloping ground, as you can see, with around over 20% of a steep terrain of over 30 degrees. So about the ground condition, well, we are, for most of the places, we have underlaid by a thick weather profile up to 60-meter thick for granite or even thicker. So in other words, pretty simple. The developments in Hong Kong actually are essentially surrounded by soil slope, with some of them are steep ones, so which is more susceptible to landslides. So apart from this is again about rainfall. Okay, just like in Malaysia, but in Hong Kong, we are in a subtropical climate areas. So Hong Kong is also subject to heavy rainfall. As you can see that the average annual rainfall is around 2,040 mm, while the maximum is over 3,000, right? And in the wet season, you can see there are actually over 5 days or more every month with an intensive daily rainfall of 40 mm or more. This is very wet weather, you can see. So the next question is, well, is the rainfall has a direct relationship with landslide? Well, of course it is. So here is the statistic of the rainfall against lump of landslide we have over the past years or so. It is broadly established that the heavy rainfall is a key contributing factor to the likelihood of landslide, as so as to its risk. Well, so but here comes another factor is the urbanization. Okay, in the old days before 1970, as the history of landslide risk in Hong Kong that has been broadly introduced by Hong Kong GES President Dr. Andy just before. Well, the slopes and retaining floors in the old days, actually, commonly they were formed improperly as part of urban developments, such as building roads or other residential buildings. Well, as you can see, well, new developments in a sloping ground setting like this will usually involve cut and fill slopes. In this case, if they are not properly formed, whether it's design or construction or both. So if, let's say, for the cross section shown here diagrammatically, in this case, if either or both of these slopes go wrong, the landslide risk is immediate because there is just the building or facility located right next to it. So as a result, I would say that based on the factors we have just mentioned, the landslide risk is high, and there were actually a number of catastrophic landslides occurred in Hong Kong, in particular in the 1970s in the last century, like the Busan landslide and the Samoping ones. Some of them with only one single landslide incident causing over 70 deaths. Okay, so this set the scene of the high risk of landslide in old days in Hong Kong. So just because of the high risk of landslide, at that time it called for the Hong Kong government's action to work out how to tackle it. I believe in that time, the government's plan is to tackle it in a way it is not only a one-off operation, but in a systematic manner to bring down the landslide risk in long run. This is the so-called slope safety system that we have today. It is a long-term commitment, and I believe it's a huge social investment so far. So to some extent, put it this way, such a slope safety system also gave rise to the growth of the geotechnical profession in Hong Kong. I would say that. Okay, so here is where we are about the slope safety system and how we bring down the risk. I believe that our system is best illustrated with this diagram. Okay, historically, before the 1970s, we have just seen those photos. The landslide fatalities were very high. The risk could have continued increasingly due to population growth, slope degradation, etc. if we had not done anything. But just at the year of 1977, actually it came to a historical moment that the Geotechnical Engineering Office was established by the Hong Kong government, which is actually a unit manned by geotechnical professionals purposely to reduce the landslide risk. And since then, we have been adopting a multi-pronged approach to manage landslide risk. What was the mean by multi-pronged approach? That is, we have been working on different fronts altogether, such as to contain the risk from new developments, to reduce the risk on the existing development, and also to minimize the landslide consequence. By doing this all together, as you can see now, we are able to reduce the landslide risk substantially. Okay, so I'm going to talk about the multi-pronged landslide risk management approach one after another. First, we contain the risk by ensuring that the slope and retaining wall associated with new developments are properly formed, so that there are no more potentially dangerous slope to come, right? Because we say that in the old days, there are some substandard one that form that cause the problem today. So actually, we do it through different means. For example, to scrutinize land use planning, to exercise geotechnical control, and to regulate those unauthorized slope works. In terms of so-called exercising a geotechnical control, actually, the objective is to ensure that the design and construction of slopes and retaining wall are done to a required safety standard. It is both the design and construction. It applies to all developments, no matter it is a government infrastructure project or some private developments. And you can see that based on these photos, some of the building construction in Hong Kong are on steep slopes such that it deserves the tight control in order to make sure that they are technically acceptable. So as for many mega-scale government projects, like for example, highways and railways. And when it comes to some potential hazard of natural hillside landslide that could affect proposed new developments, where we regulate by requiring detailed hazard assessment and the provision of the necessary hazard mitigation measures if necessary. For example, in the form of a landslide surface resisting barrier structure. Well, actually, for mitigating the lateral terrain hazard, it's more tricky. That instead of apart from controlling the engineering design or its layout, we also would advise to propose development to locate it away from where the landslide hazard may be more severe, as you can see here. There's a hillside, right? Part of it is more hard hit by some of previous landslide, maybe in the form of generalized surface flow. So we will advise them to just relocate them a little bit further in order to reduce the risk. Okay, so apart from regulating the slope associated with new developments, we also need to deal with those slopes and retaining wall just already been formed here. But those slopes may be potentially unsafe and pose a landslide risk to those existing developments or facilities, for example, buildings, roads, etc. So therefore, we will reduce the landslide risk by upgrading the man-made slope and provide risk mitigation measures for those lateral hillside. In addition, I would say that it is equally important is to enhance the slope maintenance, because slopes are prone to deteriorate with time, right? So maintenance is also equally important as for the retrofitting work. Okay, it's about retrofitting the existing slope, right? We have been doing this continuously for a rolling program, so-called a landscape prevention and mitigation program. This one started with 2001, but our history actually can date back for decades ago. That is, to sum up, it is not a one-off, but a long-term operation covering the entire territory. Well, our target is to upgrade around 150 government man-made slope based on a risk-based approach, and also to mitigate the potential hazard of 30 number of lateral hillside catchment based on a reactive loan hazard approach. So here, what is the so-called reactive loan hazard approach? That means across all the natural hillside across the territory, we'll identify those for which the risk is higher, as evidence from some previous landslide there, as you can see the photos here. That's particular to the area that the previous landslide, so we'll opt to handle them first by building some defensive structures. So what are we doing for man-made slope is to upgrade them through different engineering solutions with respect to the different types of slope. For example, for build slope, we'll be doing the recompression or to replace with some stronger material. For cut slope, we normally by upgrading them using soil nails. And in fact, nowadays, soil nail they account for over 95% of our slope upgrading works, which is our most principal upgrading scheme. And for natural terrain hazard assessment, in principle, and if practical, I would say that we will provide defensive measures such as surface resisting barrier against the risk of landslide surface, instead of stabilizing the potential landslide sources areas uphill. So there's an example, for example, reinforced concrete barrier structure and the steel flexible barriers. There are also some enhancements such as bubbles within those barrier structure for energy dissipation. So as part of our slope upgrading works or natural terrain mitigation works, we also incorporate the elements of ecological enhancement in order to make the slope greener and more ecological friendly. And we also use some guidelines to promote greening and also the bioengineering. And okay, when it comes to slope maintenance, actually we are taking a systematic management approach, I would say, but first clearly defining the maintenance responsibility. Actually, we have altogether around 60,000 slopes in Hong Kong, and for each of them, we'll assign a maintenance party or agent who is responsible to do the maintenance work for it. Well, in principle, it's just like an asset management, right? So you can see that actually the government is responsible for the maintenance of the 2/3 of them, while for the rest, the government, but for the rest, the private owner have to do the maintenance work for them. So when it comes to slope maintenance, okay, it may appear to many that it is trivial, but actually it should be done properly if you want to make it effective. So in this regard, we publish guidelines to advise on what to do and when to do the maintenance related inspection by a suitably qualified person, and also work on the respective maintenance work to the case needed. For example, here are some guidelines showing that what to do and where, so that even for some maintenance agent who is a layman and not a geotechnical professional, they know what to do. Okay, about the multi-pronged landslide mitigation strategy. Thirdly, we are also managing the risk by by minimizing the landslide consequence. What does it mean? That is, apart from the engineering measures we just mentioned, it is equally important and effective for us to raise the awareness and the preparedness of the general public against the landslide risk and to stay away from it. Well, to some extent, I would say that this approach is more people-centric and cost-effective because it doesn't need huge capital investment actually. So what we have been doing are to clear the squatter from hilly terrain with vulnerable structures, provide landslide emergency services in order to minimize impact and damage. Also, we will issue the landscape warning to the general public to alert them and to educate them on the precautionary measures. But in Hong Kong, we have a landscape warning system here, for which the warning is issued by the Hong Kong Observatory, like other weather-related signals, in collaboration with the CEO. It aims to alert the public on the risk of landslide at the time of heavy rain, and whether or not to issue the warning and when to issue it actually based on the rainfall intensity by the rain gauge across the territory. Well, based on our experience, this warning system is quite promising. Why? Because it is promising in alerting the public because actually most of the recorded landslide that had been occurred were occurring at the time when the warning signal is closed. So that means the rationale the rationale we have been putting in for the landscape warning is quite effective. So this is about educating the public on the precautionary measures. We aim to arouse the public awareness and to foster public support on the slope safety policy. Well, we do this by through different means, for example, publication, social media, and also some outreaching activity, for example, the exhibition or some school talks in order to raise the public awareness against the landslide risk. Okay, so actually all I have said is the Hong Kong slope safety system today. But in fact, it has been working quite well, which is globally recognized system of its kind. And we have managed to bring the landslide risk to a reasonably low level over the years. So everything is fine. But that said, our landslide risk management keeps going because the risk is never be zero. And indeed, there are many evolving challenges ahead that we have to meet. So first of all, is the climate change, right? Which affect everyone around the world. In Hong Kong, in 2015, Hong Kong also issued its climate change report to address this issue. But as we all know that the impact of climate change is wide-ranging and far-reaching. It could be includes global warming, rise of sea level, but with respect to landslide risk, perhaps the most prominent one is the extreme weather and rainfall. So with the extreme rainfall, the effect on the rainfall is not only the increase in the frequency, but probably become more acutely intense during rainstorm, as you can see here. Well, the peak hourly rainfall, say in a particular rainstorm, just will keep rising with time, okay, up to 100, around 150 mm per hour. So this is, I can say that the effects of climate change and extreme rainfall is evidential, but not speculative, as someone will argue. So ultimately, what is the effect of the extreme weather and rainstorm? That is more landslide, and if there's landslide in a larger scale, and with the landslide mobility there is become more mobile. So to summarize, that is, the climate change will make our landslide risk higher and higher. Okay, so here is another challenge, again about climate change, but this one is about the mission towards carbon neutrality, which is a global mission to all, right? So in the year 2021, that is 2 to 3 years ago, Hong Kong also put it in our agenda officially and set the mission and vision so as to align with the international ones. Okay, we are also in the agenda to cut and to reduce the carbon emission per capita and also for Hong Kong society at all. But the question is, okay, what does the carbon neutrality has to do with landslide risk management? It seems that two things are unrelated. Well, I'll put it this way. The carbon neutrality roadmap sets out the target for the emission reduction, right, by 50% by 2035, and hopefully to achieve net zero by 2050. So in fact, actually, in terms of carbon emission sources, one of them is the construction-related activities. And in this context, it has something to do with the landslide risk management, because even though we are not very carbon intensive, but because our work also involves engineering construction works, especially our slope works, lies across the entire territory, and also it's a long-lasting work. So we have to do something to align with the carbon neutrality. Okay, and lastly, the last challenge is a societal one that is facing all industry and sectors, not only about the work related to landslide risk management. That is, we are running out of talents. We need professionals for planning, investigation, design, analysis for landslide risk mitigation measures. And also, at the same time, we also need workforce, but the challenge we are facing is the talent shortage and also the aging workforce. So with respect to all these challenges, that we are moving ahead with our landslide risk management with many now at the objective. I would say that our work in terms of landslide risk management, we have to keep doing this, but now we have to do it and make it more data-driven, fast and reliable, resource efficient, more accessible and sustainable. Okay, and in response to all of these objectives, the landslide risk management work that we are doing now, we have to work in a smart and sustainable manner. Okay, some of the works are just like what it has to be in the old days, but we have to do it along these two new directions. Okay, actually, in Hong Kong, VGEO have been moving ahead along this direction with many initiatives. Here, I just brought for the purpose of this speech today, I just broadly categorize them in the 3 areas. I'll briefly talk about it one by one quickly. So first of all, it's about the geotechnical information infrastructure. The way we call it an infrastructure because it is actually not only a database. Okay, actually it is a platform that integrates a series of separate information system related to landslide risk management, and each actually carries its own function. By doing this, it actually has enhanced the accessibility, efficiency, and the data sharing. But this synergy is very good that now we are able to not only boost the productivity, but also contribute to many improvements in between the system. And one of the systems in the infrastructure platform is our slope information system, SIS, which is a very resourceful and informative database containing all the essential information of all slopes in Hong Kong. For example, geometry, location, and even some documentary record of its history. For example, its previous study, construction activities, and landslide. Well, in other words, it is a one-stop shop for all the users to access all the slope-related information. Well, I can say that, well, as one of the geotechnical professionals in Hong Kong, I'm a frequent user of this information system. This is really a big piece of work, I can say. In fact, I believe our geotechnical profession in Hong Kong has also benefited a lot from this system. And what's more is the system can be is accessible through a mobile app. Nowadays we all stay with our cell phone, right? But accessing through the mobile app will make it become more convenient and more productive. And the apps is not only confined to the slope information system, but many other systems. For example, the landslide warning and landslide information system. Especially for the landslide information system, some of us have to do some field work outdoors when they have to deal with the landslide. So being able to access information through mobile web is very powerful and effective. And also, we also developed a city resilient platform, I would say, called a common operational picture, which centralizes the emergency action by different government departments. But this is important and very useful because very often joint action is required among different parties. For example, a landslide could affect the traffic of a busy road, or that could block a major drainage and give rise to flooding. So this information, collaborating different parties, is very useful. And so the slope information system I have just introduced is not confined only to the people working in the government or in the profession, but it is also accessible by the general public. It also contains many information visually and also in text, so that for those who want to know more, it is very informative and it's very readily accessible. So next, I would like to talk about, apart from those information system or infrastructure, we have been actively adopting digital technologies and digital transformation for a range of tasks and activity throughout the process of landslide risk, from planning, investigation, through to the long-term monitoring. Here, I will try to highlight a few examples. The first is our actively use of remote sensing technology. Actually, we have been doing the airborne LiDAR survey first, just to collect the information. And we have been doing this for over 10 years, right? Just in the year 2020, we have done the second round of tertiary LiDAR survey that have collected a wealth of very useful data sets for the terrain, right? So you can see that actually the result of the most updated LiDAR data set can produce a digital terrain model which is able to show the important topographical feature which is with an inequality comparable to the aerial photos, at least for planning and design purpose. This is very useful. And another example, apart from the application for design and investigation or planning, we also do the airborne survey for new development project. As you can see, is able to create a digital terrain model to a mega project design. So apart from planning applications, we are also actively using droning and remote sensing technology for landslide investigation. So here is a landslide occurred in the 2021, just 2 years ago. Well, the landslide scar is hardly accessible, right? So the advantage when doing the landslide investigation, the advantage of using drone and LiDAR is that we are able to collect the data and build up the model very quickly, but at the same time with a reasonably high level of accuracy in order to enable the follow-up action to proceed very timely, isn't it? And then you can see that the outcome of the LiDAR survey is like this. Okay, it's very useful for us to do a subsequent investigation. And then it's about the BIM. Well, BIM was first developed for building projects, as its name suggests, but nowadays it's widely adopted for different areas of engineering construction, right? The landslide prevention and mitigation is no exception. So indeed, there are increasing use of BIM for landslide risk mitigation that offer many benefits. For example, we are able to use the BIM to aid our design, cost estimation, for example, in a crash analysis. Here is the example of the BIM for soil nailing. And then another example of the digital technology is the smart surface resisting barrier system, which employs Internet of Things technology. In this case, actually, we have built a reinforced concrete structure to protect the Green Mary Hospital from the potential landslide hazard from the catchment you can see here. Well, at the same time, the structure functions to resist and retain the debris. But at the same time, we also install a sensor such that it can detect and then signal the real-time landslide that will happen. So here is the sensors. So likewise, sensors cameras are also used for the steel flexible barrier for real-time detection of the landslide. And the beauty is that this landslide detection system equipped with the sensor is also accessible through the mobile app, so you can get the signal in real time through the cell phone. Well, and lastly, I'll quickly go through the sustainability strategy that we employ in our landslide mitigation measures. So working towards the net zero carbon emission targets, we first start with to embrace the guiding principle of a low carbon design and construction. And along with this direction, we then will explore and formulate the carbon emission strategies. And then finally, to materialize this by implementing this in the slope operating works. Actually, now we are in the way to formulate.
Yeah, Roy, sorry to interrupt.
Hi.
I think appreciate you can wrap up in 2 minutes.
Okay, I can. So actually, we are on the way to formulate our strategy by getting the baseline intensity, to set the targets, set the roadmap, and to determine our decarbonization measures. So in the interest of time, perhaps I'll skip here. There is some preliminary work that we have been done. We try to categorize that. Well, the most sensitive area of work that we are able to decarbonize our work in a more effective way. There are many different aspects that we will be exploring to decarbonize. Well, one of the ways is to promote wider use of green energy. I believe many people in other sectors are doing that. So hopefully we can identify that scope in our slope stabilizing works that we can utilize the green energy options. But compared with green energy, actually the prospect of using greener construction material is more promising in our agenda. Actually, in Hong Kong, we are now moving ahead with using more environmental friendly supplementary cementitious material to replace cement. And other options that are upcoming is the so-called green steel and the carbon capture and utilization and storage measures. And lastly, in terms of decarbonization, we also carry some trials or some nature-based solution, for example, to the bioengineering to improve the landslide scar instead of inputting some man-made material for the stabilization measures. Okay, so in the interest of time, here are the key message of my speech today. That is, well, our landslide risk management in Hong Kong actually is a long-term commitment because there's never be a zero landslide risk. So I can say that actually landslide risk management is an endless battle. We have been adopting a multi-pronged approach doing that. But at the same time, we are facing an increasing challenge. So looking ahead for what we are going to do to manage landslide risk, actually the two major trends are to accelerate the application of smart technology and to embrace sustainability when we do our landslide mitigation work. Okay, so actually we, the GEO in Hong Kong, are going ahead with many different evolving smart and sustainable initiatives. Just have a glance here. So that's the end of my speech today. Thank you.
Thank you, Engineer Roy. So I think the question, we'll take it during the panel discussion. So for the audience, if you have any question, you can post it in the Q&A button. So for our next speaker, let me share you his CV. Our next presentation is on landslide risk management in Malaysia by Engineer Dr. Lau Tian Huat. So Engineer Dr. Lau graduated from University of Malaya in civil engineering in 1994 and joined the research team in University of Malaya to carry out research on unsaturated tropical residual soil under the PLUS IPT research grant. Subsequently, Engineer Dr. Lau pursued his postgraduate study and obtained his master's degree in 2001 and PhD in 2011 from University of Malaya. And currently, Engineer Dr. Lau has been working in Muhammad Asbi Associates Sdn Bhd since 2002, and he has been appointed as partner of the firm. He has published more than 50 papers in journals and proceedings for local and international conferences. So I'll pass on to Engineer Dr. Lau. Thank you.
Thank you, Dr. Gui, for the kind introduction. Let me share my presentations. I'll try to wrap up in 50 minutes. I don't know whether I can do it in 50 minutes. So before I start, okay, can you see my slides, right?
Yes, we can see your slide.
Yeah, very good morning to all the fellow engineers from Malaysia, right, and also from Hong Kong. Right? My name is Lau. Right? Let me share some of my experience in landslide risk management and assessment for the past maybe like 20 over years, all right, until today. Just some of my works done, all right. Now, before we talk about landslide assessment, there are a few questions we would like to ask. For example, do we know how many slopes we have, right? Where do the slopes occur? And the landslide susceptibility, where and when could the landslide occur? And landslide hazard, what is the likelihood for landslide to occur? And also what is the consequences, right, to the landslide have, right? So definition, I think just now Dr. Ahmad Shukri have actually been us through what is the definition of landslide hazards. Apparently it's the probability of occurrence, right? And some say it's a likelihood or potential damaging landslides. These are some of the landslide hazard definitions. At element risk, we're talking about the populations, people live around the slopes, building, and all these economic activities, and that is actually the element risk. And when we talk about the vulnerability, there's a degree of loss, all right, to the element risk. For risk, basically is the product of consequence with the hazards, right? So there are some other specific risks, total risk, right? So there are some definition of risk here, right? I'm not going to go through in detail, just like to bring you along as we go into the topic of risk management. Hazard assessment methods, right? There are three main methods of hazard assessment, right, in Malaysia. Particularly individual slope assessment, that is the bread and butter of geotechnical engineers, right? And then there is linear base, that is for all the linear infrastructures, the road, highway, infrastructures like power cables, right, transmission towers, right? These are more towards linear based assessment. And then we have area based assessment, that is actually for an area, right, for particularly for developments, all right, and so on and so forth. Method for landslide hazard assessment, we have three main categories. One is using the normal geotechnical approach, where we run stability analysis and we get the FOS, factor of safety, and then we look into the hazards, which is the likelihood of failures for slopes. And then we have a direct methods and indirect methods. Geotechnical approach, as I said, is for individual slopes, all right? You run for specific projects rather than a regional studies, right? For example, slope failures, right? A slope for developments, right? You need to get to know the hazards conditions, to know the stability conditions. We go through geotechnical approach. Direct methods, these are the methods applied, right? When we actually particularly, we go on mapping works, directly facing the slopes, where you're going to have geomorphological mappings, you're going to carry out geological mappings, and things like remote sensings, right? And the methods produce landslide maps, which it can convert into hazard maps, right? And then through appropriate subdivision and zoning activities. Indirect methods involving, this is actually quite famous or quite normal way of doing hazard assessment now. We're using GIS, Geographical Information Systems. We're using statistical approach, and we're using some of the statistical approach for examples, all right? From a very simple like pairwise to neural network to the more advanced, which is artificial intelligence, or some people call it the subset of artificial intelligence, which is machine learning approach. Right? These are some of the new approach that we are actually venturing into it now, currently, for some of the projects in hand. Right? Now, selection criteria, Landslide are local phenomena. All right, it's controlled by a lot of large variety, internal and external factors. But the choice on what method to select is all subjected to the information you have, the data that you have. Right, there is no once and for all methods to actually carry out hazards. Right, so it's subjected to whether you have sufficient data, you have sufficient failure records, failure histories. Right, these are the main ingredient, right, for a good hazards slope landslide hazard assessment. Slope management systems, right? Effective slope management system requires some of the information. These are some of the information if you want to have a very good effective slope management system. Then there are the following questions that you have to ask. How many slopes do we have along this highway? Now, sometimes when we have a road, we don't even know how many slopes we have, how many cut slopes we have, how many natural slopes we have, how many embankments we have, right? So these are the first question we have, right? How many slopes do we have along the highway or along the road, right? Then how many slopes with instability problems we have to identify, and where do we have urgent issues, right? And where do we like to experience problem in the future, and what should we prioritize? For example, the budget allocation, right? Where do we start first, or which slope do we actually start to strengthen first, right? So these are some of the questions you have to ask when you come to a good, effective landslide management systems, right? So to answer this, we need to develop an asset database, right? To answer more complicated questions, right? Then we need to actually having data integrations and processing and analysis to be carried out. Right? Slope management system is a tool to help answer such questions. The output of this management system, you can use it for routine maintenance management, right? Simple things like you know where is your rock drain, you know where is your slope with erosions, you know where is the slope you require the surface protections, and then you know where is the slope you require upgrading, all right? You identify where is the location and what is the quantity like, right? And prioritize the work. There are some slope management system in Malaysia, all right? These are some of my collection, I think about 10 years ago. 10 years ago, there are some government departments, there are some highway concessionaires, like JKR, we have several systems, right, in hand, like SMS, MEMS, SPRS, SMART, all right. There are a few systems with different approach, right, adopted by Public Works Department. And we have Jabatan Mineral and Geoscience, which is the Geoscience Department, all right. We have terrain mapping, geological mapping, and currently they are actively carrying out some area-based geohazards mapping, right, in the country. MARCRES, we have NADI, and other departments or universities, right? They have NASAC, and for highway concessionaires, right? We have EMAS, TEMAN, and DSLO for MTD. Right? These are some of the existing inventory system or management system, right, by various agencies, right? So these are the system they have. I'm not going to go through this, all right? Now, this is a good example when you have a so-called risk assessment or risk management system in place, right? Now, this is one of the records from the East-West Highway, right, on the expenditure on slope repairs, right, and slope maintenance program. Now, if we look into 1993 to 1996, this is where the systems of slope management, risk management was in place for 2 years. Right, you can see that the cost of repairs, cost of maintenance dropped tremendously. All right. Now, subsequently, after that 2 or 3 years, right, that team was actually taken out. The cost of repairs actually start to go back again. All right. So you can see how effective is the implementation of risk management, landslide risk management in the road. Right. Now, this was actually taken by the papers called by engineers Muha back in 1997. Now, private sectors, we have done some work for private sectors like Genting Highland, Resort World, our famous casino on hill, correct? And then we have Petronas gas pipelines, Sabah Sarawak gas pipe have done that. Petronas gas pipe for Kerteh, Terengganu State, and also currently just completed my studies for another new highway, which is a Suka highway. Right? Area-based assessments, I have actually completed Penang Island, the entire Penang Island, for Public Works Department, JKR, all right, and then the Selangor States for Mineral and Geoscience Department, Bukit Kelana Miri in Sarawak for JKR, and also Genting Highland Land Bank, all the land on Genting Highland on behalf of Resort World Malaysia. Now, effective landslide risk management. Now, these are one of the best which we actually look into it. We review, all right, we review the Sabah Sarawak Gas Pipe Geohazard Management Practice, all right. They have a very good practice called IMMR here, all right. That is stand for inspection, monitoring, maintenance, and repairs, all right. The inspections to carry out regular inspection with area civilians, all right. Then they have light detection and ranging using LiDAR to capture all the informations. They carry out geohazard risk assessment. They have instrumentations, right? Instrumentations, including INSA, right? INSA using satellites. Development of web-based geodatabase to store, manage, and to retrieve data for all these gas pipeline. I think maybe J. Johan later will actually brief us on that. Strengthenings and repair works. That is actually some of the approach, right? We call it as IMMR, right? For geohazard management practice. These are the roadmap for IMMR for Petronas, right? You can see, all right? So until all the way to, you can see using LiDARs, then using field mapping works, then they categorize the slope with hazard and risk, then they start all the repairs and strengthening works. These are some of the example of area-based assessment. This is one of the area, I call it as the ring of fire of landslides in Kuala Lumpur, right? Hulu Klang area where there are numerous landslides actually reported, and method we use same thing. We adopted LiDAR for base map, and then we use GIS, right? We actually produce the hazard maps, and then the final product is actually the risk map. This is for our Public Works Department. The Penang Island, right? The Penang Island. We have also carry out the risk and hazard assessment for the entire Penang Island. All right, these are the hazard maps and also the risk map for Penang Island. If I'm not mistaken, this was carried out back in 2008. All right. Also, the base map was actually conducted using LiDAR, right, for the entire island. I'll give you some examples on systems that we have produced and we have actually implemented. One of it is smart systems, right? That is back in 2002 or 2003, I think about more than 10 years ago. And then the Genting slope management system for Genting, right? Just some short on that, all right? These are the architectural layout of the systems. We have spatials, we have non-spatial data, all actually in the database. And then we have a risk ranking, and then go into the TSR server. TSR stands for Temporary Sandakan Projects, right? A road back in East Malaysia, right? So we have a different level of user. We have client PC, and we have people who actually do the calculations and do the analysis. Different level of users, right? And from the smart systems itself, right? What you can see, you can actually retrieve a lot of things from the smart system, the database of it. Each and every slopes, they have a database, right? And then they have all the drainage conditions, they have the surface conditions, everything will be in this database. That is actually from the main performance recorded in the database. These are some of the system analysis systems you can retrieve from the database. You can actually plot out where is the location. You have broken drains, where is the location you require to do surface protections, right? They can plot graph, right? So these are some of the simple systems that are available in the smart system. Smart stands for slope management and risk tracking system, right? That's why it's called smart. Example of the risk map, hazard maps, right?
Sorry to interrupt, Dr. Lau.
Yeah.
Appreciate if you can wrap up the presentation. Thank you.
So So Genting one, same thing, right? This is actually for private entities, right? These are some of the maps in the Genting, hazard maps, right? Risk map. And then real-time monitoring systems of rainfall. We have actually installed quite a number of rainfall for Plus Highway. If I'm not mistaken, Plus we have about 85 numbers of rain gauges along Plus Highway. And we have some rain gauges for Genting Highland Resort World, about 8 numbers of them. Okay, these are some of the examples, right? So we have installed many years ago. I think the threshold was actually installed with threshold back in 1995. Then the threshold review back in 2008. Right, these are the location for the Genting Highland, right? Some rain gauges. The threshold we use actually is based on 1995. There's one massive debris flow occurrence, and then within the 5 kilometers radius, we have hundreds of landslides occur. Right, based on the data, we produce these rainfall threshold. Right, you can see we have landslide threshold, we have critical threshold. Right, so these are threshold. Okay, one very serious incident happened back in 2021. During that rainstorm incidents, we have about 200 landslides, right, happened on Genting Highland, all right? And I'm not going to go through in detail. Maybe I can show you some of the photographs, all right? Not only Genting Highland, but within that 5 kilometers radius on the government roads, there's a lot of landslides actually occur. Right, these are some of the recorded photographs. We actually drive outside the Genting Highland, right, Bentong, Kuala Lumpur Road. Right, there's a lot of landslide happen. Right, and for your information, the threshold actually triggered before the landslide happened. All right, these are some of the rainfall recorded for 3 days and 6 days. Right, this is only 2 rainfall records that we actually I show it to you. We have about 8 rain gauges along this Genting Highland as well. So conclusion is that to know the hazard and risk level for road slopes, it is actually crucial, right, for landslide risk management systems, right? So you have to know, right, what is the hazard and risk level, and then for effective geohazard management systems, as I said, for all the systems that we have gone through, IMMR is a quite important approach where you have inspections, you have monitoring, you may do maintenance, and there's a repairs, right? So I think I will stop here. All right. So thank you very much for inviting me to give a talk. All right. Thank you.
Oh, thank you very much. Engineer Dr. Low is a wonderful follow-up to the ideas of the risk assessment and management covered by the Malaysian and Hong Kong authorities. So next up, we have our next speaker, who's going to be Engineer Dr. Clarence Choi, who is currently an assistant professor at the University of Hong Kong. His research interests are in slopes, landslides, and ground improvements, and he has won many awards recently. So some of them include the 2023 Young Engineer of the Year Award by the Hong Kong Institution of Engineers. He also won, well, he was also the 3rd Hutchison Lecturer by the Federation of the International Geoengineering Societies, and he also won the 2022 Audrey Hunger Award by the International Consortium on Landslides. So may I pass it on to Clarence, who's going to present online. Clarence, please.
Okay, thank you, Andy. And thank you to the Malaysian Geotechnical Society for organizing this joint event. So today I'll share with you some research work we've been looking at, particularly whether we can use the effects of forests to enhance mobility assessments, and perhaps it can be a natural barrier against flow type landslides such as debris flows. So before I start off, I just want to share what the existing art is for physical countermeasures. So we might install these rigid reinforced barriers at the end of a catchment to catch a particular debris flow. These are quite massive structures that are reinforced, and they might not be so sightly. And with the advent of sustainable engineering, these may not be the best options. Of course, we've tried to improve the state of the art by moving towards more compact structures such as flexible barriers. You can see them installed on the hillside here. But nevertheless, it would be nice if we can look at leveraging the effects of forests and understanding whether they provide additional impedance to flow-type landslides. So to the main point of today's talk, well, the question impressed upon you is, well, do forests act as a natural barrier against debris flows? There are several factors we have to consider. Particularly, this is a complex problem owing to uprooting, wood-laden flows, irregular tree patterns because trees grow as they wish. We have erodal soil bed, complex flow compositions, and sometimes even boulder enrichment. So we wanted to tackle this problem by developing high fidelity numerical model first. Using idealized situations, and we want to progressively ramp up the complexity. So today I'll share with you some of the work we've done up until the effects of uprooting. So to start things off, we have no idea what the expected kinematics should be. So we start off with an idealized lab scale forest here using very simple flows, dry granular flows, which are more or less scale invariant. So you can see the differences at the bottom of the slide with those GIFs. We have a sparse model forest and a dense model forest. And you can see that as the granular flow propagates through the forest from left to right, there are unique localized changes in velocity and flow depths around the tree stems. And the patterns are quite dispersed and the density varies spatio-temporally. So it's not quite easy to investigate this problem. To help us understand and capture the kinematics, we resorted to leveraging machine vision to digitalize our experiments. We essentially use a sliding window and FCNN to turn all the frames from high-speed cameras for the physical experiments into some sort of numerical interface so that we can use it to calibrate numerical models. So essentially what we did was we took our experiments, captured the flow profiles, and came up with a digitalized overlay. And although this overlay is useful, it doesn't have any constitutive behavior. So with that said, we adopted a GPU-empowered material point method framework to give our digital overlays some constitutive behavior. We use a Drucker-Pracker criterion, and we have gasification effects. And for the flow, we adopt a mu-I rheology. To model tree, stem, and debris interaction, we use NPM-DEM coupling. So we can leverage our digital overlay to calibrate our NPM solver. What you see here is two different cases for two different inclinations. The red line is the experimental overlay and the blue is the NPM. And of course, we can use a genetic algorithm to calibrate the parameters to ensure a high fidelity model. And we can, of course, adopt more complex tree configurations. Here we have a staggered array. On the left, we have a shallower inclination of 20 degrees. And on the right, we have a slightly steeper inclination of 24 degrees. The red line, of course, is the experimental digitalized overlay, and the blue is the NPM model. And although the front is not entirely similar, I think the calibration is good enough for the time being. So once we have a calibrated model, we can start to break this problem down from a fundamental point of view and look at idealized configurations first. Of course, you may be saying trees don't have this kind of pattern in the field. Well, of course, but it's always nice to start from simple to look at idealized configurations. But it's also worthwhile to mention that cultivated forests for hazard mitigation are very much installed in regular arrays. So this is not entirely unrealistic. You can see something interesting here from this GIF. Notice how the trees here actually provide some sort of self-channelization effect for the flow, the green part, and it can actually enhance the momentum, concentrate it, and enhance the mobility of these flows. So this is quite interesting to see that tree stems can actually increase the mobility of these dry granular flows. So if we increase the density of the forest for a regular rectangular array, what do we see? Well, we still see the same effects, the self-channelization effect and the conservation of momentum in the middle and higher mobility. But of course, we don't have high pressure gradients from thick flow depths driving the flow out. So it's quite dispersed, the front that you can see at least. If we look at more complex configuration, staggered arrays, as shown on this particular slide, you can see staggered arrays are very good at dissipating energy and spreading the flow laterally. And it does eventually arrest the flow here. However, if we zoom into these staggered arrays, we do see the same effect happening. There's a self-channelization effect caused by these regular patterns of tree stems here. So this was quite interesting for us to see that, contrary to what we thought, that forests are always excellent at impeding debris flows. In this case, there's a bit of an impedance effect that is not entirely true because of channelization. So in much brevity, I just want to say that although in some cases, forests can reduce the mobility of flow, there are some cases where it actually enhances the mobility of flow. Through scaling, we can show you this graph on the left, normalized runout distance versus some characteristic length scale. Anything above the reference line that's dashed here above it shows that the mobility is actually increased due to the effect of the forest. And we need to be cautious when we're designing cultivated forests for mitigating flow type landslide hazards. So we first looked at tree spacing and patterns, and then eventually we looked at uprooting. So it's actually not that easy to model uprooting. The uprooting process is simple. You can provide some sort of resisting moment or bending moment for uprooting, but the main problem is how do you model the stems after they're uprooted in a physically correct manner. Classical spherical DM is quite easy to deal with. Contact detection and penetration very well defined. You have a single point for the contact. Normal contact force doesn't really generate rotation unless you want it to. However, stems and DM are a little different, as you can see here. There's several questions that pop in our mind, particularly contact detection is complex, non-spherical. It's difficult to get the contact area. We call this the contact manifold. And it's unclear what normal forces are generated after contact. And the resulting rotation is also unclear. So we embarked on a journey to come up with a high fidelity numerical solver that can capture stem-stem contacts and MPM stem contacts. So we essentially adopted some video game algorithms, Gilbert Johnson, Carthy algorithm for contact detection, and then we can use a level set DEM to get the contact normal and contact patch, which allows us to get the contact force and moment. And if we update position and rotation using a quaternion approach, we can, in theory, get the right physics. So does this method work? Well, there are some benchmarks. For example, we need to check if we have the conservation of momentum on the left. And in the middle, there are analytical equations to see if we've captured the correct rolling and sliding behavior. And on the right here, these two graphs show us, if we compare the dash curves and the data points, we can see that we're not too far off. Some discrepancies are due to damping required for DEM. So with the correct physics, we can move on and look at uprooting. Here's the same setup, experimental setup I showed earlier. This is a dry granular flow moving through the same staggered forest configuration. And in this case, I gave the tree stems no uprooting resistance. I just used the inertial component of the tree stem to resist this granular flow. And it's quite interesting. If you want to put in uprooting resistance, you can put it at the base as some sort of bending or impact resistance. That's quite simple to do. But more importantly, we have to try to evaluate whether the post-impact tree stem flow interaction is correct. Well, we need to work on that. That's not entirely an easy problem to deal with. But some preliminary thoughts. If we compare kinematics of flow forest interaction without and with uprooting, so on the left here we have without uprooting entirely rigid stems, you can see that in the early stages of impact, you get this kind of pattern here on the left, and we compare it at the same time frame for with uprooting, but with zero strength. The inertial component of the stems is actually sufficient enough to create a very similar pattern during the early stage of impact. And more interestingly, if we allow the simulation to progress a bit further, we can see the front starts to differentiate itself. So the stems mostly influence the frontal kinematics and dynamics of a flow type landslide. And if we want to further look in this problem and compare, here's a apple-to-apple comparison of what happens if we ignore the effects of a forest in the mobility assessment on the left. So this is a clear board without trees, and this is the deposition. I increased the friction significantly because of time constraints to present these findings to you today. So that's on the left with no forest, and on the right, if we have a forest, but with no uprooting strength. It's quite interesting to see that the forest here actually creates a negative effect on mobility. We can see that the flow, it's to scale here, actually travels further for the forest case due to concentration of momentum. And also, it's unclear what these stems are doing, but you can see the cluster of stems here are actually driven out much further to the right. So there seems to be a negative effect caused by the forest. And the main take-home message that we found so far, based on some preliminary research, is that forest and uprooting may not always have protective effects against flow-type geohazards. So if we can further improve our modeling capabilities, perhaps entrainment, boulder enrichment, biphasic flows, maybe we can start to back-analyze field cases and try to understand the true effect of forests as a natural barrier against flow-type landslides, such as debris flows. Some preliminary findings with my collaborators, Dr. Jin-Hung Chu, and my PhD student, Yang Zhengyu, is at the bottom here if you're interested. So as promised, I will finish early, Chairman. Thank you.
Thank you very much, Terence. That's a very, very interesting topic and also wonderful numerical simulations. I'm sure we'll see quite a few questions from the audience on this. But then again, like I said, we're going to leave the Q&A section towards the end of today's event when we have a panel discussion. So now let's take a short break because we have a bit of an overrun. So we will also cut short our break to 5 minutes, and we're going to resume at 11 a.m. in here. Thank you, and see you in 5 minutes.
Hi, welcome back. I think thanks for this short break. We will now resume our next presentation on leveraging on machine learning for managing geohazards impacts to structural assets by Johan Rohani. Sorry for the interruption. Johan Rohani obtained his Bachelor of Engineering from Queensland University of Technology, Australia in 1996 and Master of Science from University of Warwick, UK in 2006. He has over 25 years of experience in the field of geotechnical and structural engineering with involvements in related projects, both locally and internationally. He has extensive experience and is specialized in offshore geotechnical engineering. Over the last 10 years, he's also actively involved in onshore slope-related geohazards assessment works. Besides consultancy projects, he has been involved in various research projects in the area of shallow gas on soil, hull aging, remodeled soil properties, lateral soil stiffness, predictive analytics, use of machine learning and remote sensing methods for geohazard assessment, etc. Johan has published in more than 25 international and local conferences and also involved in reviewing international journals and conference papers. He is a working member in the ISO Marine Soil Investigation, API ISO WG10, Foundations and Standard Malaysia Offshore Structures Technical Committee. So now I hand over to Johan. Thank you.
Okay, Dr. Gui, thank you so much for the introduction. Let me share my slides. So again, thank you very much to the Malaysian Geotechnical Society and the Hong Kong Geotechnical Society for organizing this joint forum. So my name is Johan. I'm actually from Petronas under the Group Technical Solution. Actually, this presentation couldn't have been prepared without a lot of support from my colleagues listed below. And also some of the participants here also that I'm aware of, like Dr. Low and RLU has provided us a lot of help over the years to help us where we are now. So the topic of my talk today is leveraging on machine learning for managing geohazard impacts to infrastructure. As an objective for today's talk, I like to not too much detail on machine learning, but to also share with you some of our challenges facing with managing our pipeline asset, which is located specifically at high elevations and remote location. As you can see in this slide, relatively the Petronas Twin Towers, where we work, is about 1/3 of the overall of the highest elevations that we have our pipelines, and our pipelines are located in Sabah and Sarawak. So as context setting, why we are trying to implement machine learning. So the motivation for this is that because we have our pipeline located in a mountainous region, over 1,000 meters above sea level. We have 512 kilometers of this pipeline with dynamic ground conditions. We call it dynamic ground conditions because like some of the previous presenters have alluded to, we are facing rain effects and climate changes that are affecting our ground conditions. And if you can see, if I can just highlight the picture here. If you can see, our terrain is essentially in mountainous. There's not too much accessibility. So we have a tough time trying to access this location. Even to assess the location, we have to manage the access route itself, which are also in mountainous region. So as you can see, there are challenges that are a bit different from what we are facing maybe in normal conventional roads infrastructure. So our issues is that these geohazard impacts are impacting our gas supply to our customers, and we have incidences of what we call loss of primary containment, essentially loss of our gas supply. And over the years, we have collected large amount of data that we could leverage on to manage this pipeline. So these are the motivation and pain points that are giving us the push to enhance our management system so that we can get better risk assessment. We can have timely trigger actions for this monitoring device and information, and we can have a prescriptive integrity management system. So I will talk to you about that in a bit detail, and I focus a bit more on the machine learning. I'm not a data scientist, but my experience with data science has been through our work on this pipeline. So as an overall architecture of our system, if you can focus on the left side here first. So there's an array of data that we have in our database, but I like to focus that in our machine learning work, we depend highly on LiDAR information and proforma. What are proformas? Proformas are actually sort of data that the geologists who goes to the site, they collect this data. So we call them proforma, which lists all the various features of the site. And we have a web portal. Essentially, the topic that I'm going to share today is about more focused towards data visualization and analysis. We have this system so that we can have make informed decision. Also to share with you, I give you some sort of a highlight of the system that we have. We also have something similar to GKR, a system that is able to, this was also Dr. Lau's idea. Each slopes have got to have its own identification number. So we manage each of our slopes with an ID number, and these slopes, depending on the risk, are visited every 2 weeks or 1 month to be assessed in terms of geohazard risk. So we have a system managing this with all the data collected, and that's where it resides in our server. But what happened is that with all this data, and because our pipeline is long and it's difficult to send people to investigate, we are beginning to see that we need machine learning to help us manage all this information and try to predict better. But what are the problems with using machine learning? So when we use machine learning, it means that we need data. And these data are usually data from the field that are in, a handwritten format sometimes, and some of them are translated to Excel, and then we have images. So we need to clean this data so that the machine learning can learn. And we have instrument data, and we have various format images also to also have a system to be able to manage. So we have a system with large amount of data, various format, and we need to train this data to understand risk. So that's issues about machine learning. So where does machine learning fit into our overall system? So we are trying to build a digital twin framework. I think this is the sort of modern terminology that we've been trying to achieve, digital twin. But I have to share with you that from my limited experience, it is quite a challenge to achieve that. So I will focus. So in a digital twin system, we need data input, we need the analysis, and we need the output, and we have to have a foundation of experts, cybersecurity, change management system, sensors infrastructure for us to manage this digital twin. But my topic will focus a bit on the machine learning portion in the analysis part of this digital twin. So machine learning. So relatively to declare, this was only apparent to us over the last few years to incorporate machine learning. So we are also relatively new in this journey of machine learning. But just to share, so for SSGP in Sabah Sarawak pipeline, we have about 20 independent parameters of variables that we call them that we need to understand. And this includes things like slope height, slope angle, signs of distress, distance of the slope to the pipeline, distance of the stream to the pipeline, right? So these are data that has been collected in the proforma by the geologists that we need to gather. And the challenge is to clean this data, like I said earlier. So once we clean this data, we have to sort of understand what this data means. whether this data, for instance, when we have a particular location with a series of slopes, what kind of distribution are these slopes showing? Are they of a certain normal distribution in terms of the slope height, or is it log distribution? So we need to make sense of that in our exploratory data analysis. And then we need to do feature engineering, because this data, it doesn't mean anything to the machine. We need to change these features. For instance, slope height. If we say a slope height is 40 meters, the machine cannot differentiate what is 40 meters and what is 50 meters. So we have to train the machine with certain sort of using our experts in-house and our engineers. They have to sort of codify these heights. So for instance, within 0 to 10 meters, it has a range. We give it a code of 1. Relatively lower heights means relatively less risk, for instance. So we have to train the machine, and we have to do feature engineering for us to get the machine to understand our data, right? And after doing all this feature engineering, then only we build the model. So a lot of our time is looking at the data, training the data, right? Testing the data before we can come up with the model, right? And then model optimization, which means after even we get the data and the risk that we are looking for a particular location, we have to retrain it. So in general, that is the machine learning general process. Okay, how it fits into our overall system. So we have what we have our pipeline has already been established many years ago. So already we have what we call a pipeline integrity management system. So now we have to integrate our geohazard management system into the pipeline integrity management system. So now we have the data source, the geohazard data that needs to be ingested and transformed, and then we have the pipeline data where it needs to be put in an input database. So we need to understand the amount of space and server database that can capture all this information before we can train it, before we can use, now we are using a cloud system, and then we have a visualization system that is incorporated into our integrity management system. So the idea is, with machine learning, who's able to now learn about this data, how this data affects the risk, that is feedback into our integrity management system. So, but for instance, if we know a certain location is high risk, the system is able to pick out how that impacts the pipeline, and even goes towards, because of that impact, we can give you the solution of what kind of repair. So we have to some degree this kind of system in place. Now, going back into the predictive analytics. So in the world of pipeline engineering, we look at what we call probability of failure to the pipeline. So there are various threats that impact the pipeline. And here you can see that geohazard is a threat, strain is a threat, well is a threat. So geohazard threat is one of the threats that is facing the pipeline. I will focus towards geohazard threat, right? And as alluded earlier, we also have a framework called the IMM framework, where we manage our geohazard threat, right? The pipeline itself has got its own inspection system. So we call the IMM framework as the geohazard threat. Okay, I've been warned that I have about a few more minutes. I'm going to go quite fast. In essence, we have a system which based on pairwise method that give us a risk rating. And for us in the pipeline industry, we have ISO 20074, which is used to derive the risk. How we translate the risk is we have a risk level that is associated to a probability of failure, and we have developed a system within Petronas where we associated the risk to a probability of failure for the geohazard, as alluded in this page. All right. This is a bit busy, this slide, but what I'm trying to express here is that we need ML Azure. We're using ML Azure machine learning to develop comparisons between models like linear regression, multiple regression, right? We need to understand whether we are having a classification issue or regression issue. Because classification is saying that, okay, how do I train my model to say it's high or very high risk? But regression is to giving it a number. So we're moving towards a regression technique where we're able to give each location a number which tells us the risk specific to a location. And we are also showing here that various method gives various accuracy. So we have to use feature engineering with various combination for us to understand the risk. Here, I'm just showing that we have been successful to when we have at site saying that location is very high risk, our machine learning say is also very high risk. But other location we are not so successful. Our machine learning saying things that are different from our site inspections. And we also have monitoring rain intensity because rain is the one that is sort of biggest impact to our slope stability issues. And what our machine learning is able to do is we're able to give risk rating dynamic every month. So we're able to change the risk dynamic every month. So we're able to now know the risk being high or low on a monthly basis. So moving forward, we're trying to understand these issues of rain, the rain intensity versus the permeability, and trying to understand what ranges of these risks are actually affecting the slope failures. We have done site validation, and we are, to me, 73% validation is an industry standard. We hope to improve this, but hopefully with more data, we can improve our estimation of our risk. We have a dashboard that we use to manage our risk. I hope I'm not moving too fast, but in conclusion, to meet the committee's timeline, I'm just to say that machine learning can be leveraged on to help with better improvement of prediction of GIZ, but we need continuous improvement. Increase automation, less dependency on human intervention, use more digital technology. We have various experiences, but we believe multi-spectral sensors will help us with use of drones to provide cost-effective and consistent data acquisition. More data with calibration, people at site. People are still very important to us to do help with the prediction and detection. With that, I think we need to invest in technology and learning for us to enhance the capability of machine learning for our system. But it is not a silver bullet. With that, I thank you so much.
Thank you so much, Johan. I hope we are not pushing you to move faster. But it's a wonderful presentation. I'm sure we're going to have more discussions during the panel discussion section. Okay, so next up, our speaker is going to be Professor Jianfeng Wang. We usually call him Jeff. Jeff is an internationally renowned expert in the field of American mechanical characterization and modeling of granular soils. He has received many prestigious international research awards, including the 2022 Fabio Fellow, the IAM Award, 2011 Geotechnical Research Medal by the UK Institution of Civil Engineers, and 2010 Higher Education Institutions Outstanding Research Award by the Ministry of Education of China. Jeff is also an associate editor of Geotechnique and the editorial board member of Computers and Geotechnics, Journal of Rock Mechanics and Geotechnical Engineering, and also Soils and Foundations. He has published over 100 SCI journal papers, and he's also among the list of the world's top 2% scientists in the year of 2022. So without further ado, I'll just pass it on to Professor Wang.
Okay, thank you, Andy. Can you hear me? Can you see my PPT? Okay, good morning, colleagues. So it is a pleasure for me to talk in this joint MSG HK GSE forum on landslide risk assessment and management. So the talk today is on limit equipment method for rock slope stability using a generalized Hook-Brown criteria. So this is a work that I have done a few years ago in collaboration with Dr. Deng Zhongping of Central South University. So this is outline my talk. First of all, I will talk a little bit about the background and introduction of this topic. Then I will present the nonlinear generalized Hook-Brown, in short, GHB. and linear equivalent mole Coulomb, in short, EMC, strength parameters in slope stability analysis. Then I will present the technical derivation of the limit equilibrium method for rock slope stability with nonlinear GHB criteria. And then I will present a few comparative analysis of typical slope examples, and then followed by the verification of the slope factor of safety using the charts generated from the proposed method. And finally is a conclusion of this study. So first of all, research background and introduction to slope stability. Well, we know that landslide is a very important and imminent issue in geotechnical engineering, which causes huge losses, some even devastating disasters to industrial and agricultural production. It's high importance, in Hong Kong, in Malaysia, and in many part of the countries around the world are very obvious. So predicting the stability of rock slopes is a classical problem of geotechnical engineering, especially in designing dams, roads, tunnels, and many other engineering structures. So here are a few ticklish issues or burning issues, I would call, of the recent rock slope stability analysis. First of all is the nonlinearity of the stress criteria. It is well known that the traditional linear mole Coulomb criteria generally does not agree with the rock mass failure envelope. Okay, in particular, when the rock mass is in a state of relatively low confining stress, okay, which is the regime where the nonlinearity is very obvious. So to deal with this issue, Hook and Brown in 1980 proposed the very famous the Hook-Brown criteria, which is later extended to the nonlinear generalized Hook-Brown criteria. Okay. However, a limitation of the nonlinear HBG criteria is its relatively complex mathematical expressions and a number of rock parameters. So this makes the nonlinear GHB criteria not being directly applicable in LEM analysis. And the inconsistency estimates of the rock slope stability, FOS, between the equivalent MC criteria and the nonlinear GHB were often as high as 64%, okay? So this low accuracy presents an urgent need for the improvement of the traditional MC stress criteria. So this is a framework of the method presented today. So it's going to be a new LEM method to analyze rock slope stability using the extended nonlinear GHB criteria. First of all, we will obtain the approximate analytical formula of the shear strength expressed in the nonlinear GHB criteria. Then this criteria expanded using the Taylor series with assumption of the stress on the slip surface. Then the static equilibrium conditions of the sliding body will be established to yield the system of linear equations, okay, of a few coefficients in the GHB criteria. Upon solving the linear equations, we'll use the stresses on the slip surface. And finally, the FOS will be calculated and verified using the known stress on the slip surface with an arbitrary shaped slip surface, which is an advantage for the current method. So here is a little bit comparison between the nonlinear GHB and linear EMC strength parameters. Okay, so this is the equation for the GHB criteria. Okay, so tau F is the shear strength at failure, and it's a function of a number of parameters, including sigma, the normal stress, sigma C, uniaxial compressive stress, MB, material constants related to the intact constant MI, which reflects the hardness of the rock, parameter S, reflecting the degree of fragmentation of the rocks, and a range between 0 and 1, and alpha, another coefficient reflecting the characteristics of the rock mass. So parameters MB, S, and alpha can be expressed as a function of the geological stress index like this. And the parameter D is a weathering weakening factor related to the excavation mode and disturbance degree of the rock mass. Okay, so here is the linear equivalent MC strength parameter, which are expressed in terms of the GHB parameters. Okay, so I'm not going to talk about the details of these equations. Okay, so and here is a comparison of the two criteria in a typical slope stability analysis. So in this diagram, there are three slip surfaces shown: the shallow, intermediate, and the deep slip surfaces. Okay, and the black curve represents the distribution of the normal stress on the three slip surfaces. And on the left-hand side is the two criteria. So we can see that in zone 1, which has relatively low normal stress, okay, we can see that the linear EMC criteria is greater than the nonlinear GHB criteria. Whereas in zone 2, in which the normal stress is relatively high, we know that the slope FOS determined by the both criteria are close to each other. Okay, so the finding here is that the linear EMC criteria overestimate the FOS for a shallow failure slip surface. Okay, so next part will be the detailed derivation for the proposed nonlinear GHB criteria. So here is a typical diagram, okay, for the LEM analysis of our slip surface. So we extract a typical slice denoted by A, B, C, D right here. So if we mark all the static forces, okay, on the unit slice, we can put down the horizontal and vertical force equilibrium equations. All right. And please note that this equation does not consider the effect of interslice forces. Okay. And from these equations, we can derive the normal stress sigma naught in this equation. All right. And because of neglecting the effect of interslice force, we can correct the actual normal stress sigma using this equation, which is equal to λ1 times sigma naught, where λ1 is a variable. So here is a detailed derivation of the criteria. So this is the definition of the factor of safety, okay, and incorporating the GHB, the conventional GHB criteria, so we can compute the derivative of the shear stress tau with respect to sigma and phi. The derivative of shear stress tau and the instantaneous friction angle phi with respect to normal stress sigma. And then we can use Taylor series expansion to expand the shear stress tau around the initial normal stress sigma naught, the initial value in this equation, okay? So the first two are the first order and the second order derivative, and the third term is the high order error of sigma minus sigma naught, where the coefficient tau 0.01 and 0.02 are expressed by these equations. And then it follows that we can obtain this equation of tau equal to lambda 2 tau 0.01 plus lambda 3 tau 0.02, omitting the high order term h. Okay, so the next step is to establish the equilibrium condition. Okay, the horizontal force equilibrium, vertical force equilibrium, and the moment equilibrium, and plug in the previous equations of the Taylor series expansion of tau. We can establish the following linear equation in this form. Okay, so with the coefficient AI being the various integral forms of these stress variables. So by solving this equation, we can attain the values of lambda 1, 2, and 3. And then we can use these two equations to calculate the normal stress and the shear stress. So finally, using the calculated normal stress, shear stress, and instantaneous friction angle, we can calculate the factor of safety using this. Okay, so more details can be found in our paper here if you're interested. So the next part is show a few rock slope examples. The first example is a rock slope with height h equal to 20 meters and rock slope angle of beta 45 degrees with the following parameters: gamma, GSI, MI, and sigma.
Very sorry, Jeff. We might have to wrap up in about 3 minutes or so. Is that okay?
Thank you.
Sorry.
So with 6 cases of the disturbance degree of D varying from 0 to 1. So this is just diagram showing the distribution of shear stress calculated different equations. Okay, so here is a table summarizing the results calculated using the proposed method and the classical method of EMC. So we have several findings. We show that the current method shows the smaller results than the LEM. Okay, and the maximum difference between the current method and the classical method is about 6.7%. And because the current method satisfies all the static equilibrium conditions, so it provides very satisfactory results. And the current method is suitable not only for circular slip surface, but also arbitrary curved slip surface. So this is second slope example. So in this example, we are back calculate the slope angle beta, GSI, and MI using the proposed method. So here is a table. So I'm not going to present the detail. So basically, we show that the results of lower bound LAM and the current method differs by less than 2%. So the next part is a show of the various charts, which is created using the proposed method. So we show the slope charts for the rock slope of GSI equal to 20, for D equal to 0 here, the first case, And here is a case for the d equal to 0.5 and the d equal to 1.0. Okay, so engineers can use these charts for the practical rock slope stability calculation very conveniently. And this is the last example showing the use of the charts to evaluate the rock slope. Okay, actually, the design of the slope to meet a designated rock slope factor of safety 1.0, 1.2. So we show that the stability of the rock slope of arbitrary slope height can be conveniently determined using the charts, and very satisfactory results can be obtained. Okay, so finally, several conclusions can be obtained. So I'm not going to read every clause. So basically, we show that the proposed method is very advantageous against the traditional LEM method, okay, in that it can deal with both slick surface and arbitrary shaped slip surfaces and provides very competent results. And it can also generate FOS charts, which can be conveniently used to analyze the rock slope stability. So that's all I want to share today. Thank you for your attention.
Thank you, Prof. Wang. So our next presentation is on landslides, lesson learned and risk management approach in Malaysia by Engineer Liu Xiaoshong. Engineer Liu obtained his Bachelor of Science degree in Civil Engineering with first-class honors from National Taiwan University at Taipei in 1991 and worked as a geotechnical engineer in Sino Geotechnology Inc. at Taipei for a year. And in 1992, he continued his postgraduate study in University of New South Wales in Sydney, Australia, and obtained his Master of Engineering Science in 1993. He then returned to Malaysia to work as a geotechnical engineer in a multidiscipline engineering consultant firm. He's a senior director, founder of GMP Geotechnics in Berhad. In the past 29 years of his professional career, he has been involved in numbers of forensic investigations of landslide problems at mountainous roads and is one of the project team members in the National Slope Master Plan study commissioned by JKR. So I'll hand over to Engineer Liu. Thank you.
Okay, very good mornings. Okay, today's my presentation maybe a bit long. I will try to fly through because I had quite a number of case study to be shared. So I think my presentation will cover 5 main points here. One, we will start off with the population growth and the land use that to see how the landslide affecting us. Then I think it will give some idea about the challenges on the landslide hazard. I'm sure that this will have been well covered by the earlier speaker. And more importantly, I think I'll try to show you some case studies that I have gone through with the various kind of landslide. And importantly, I think I want to throw some view and thought to the engineer fraternity for you all to think of, and then finally a short conclusion. I think human civilization actually you started off with a lot of land use, but of course I think in the earlier day the land use is the population is not that much, so we are able to accommodate all our activities. But with the industrialization and also the development with population growth, I think the land use is getting less and less, and we are being pressured to use some of all these more hazardous ground in the earth. So that's why I think we are facing a lot of problems that today's topic will well cover that. So from this chart, basically to show you actually how are we moving from the flat land or near the coastal area towards the hillside. But of course, I think not all the landslide will be happening always at the hillside. So long as there any differential in the elevations and the gravity will work it out to have the landslide to work through the potential energy to gain the Earth mass will gain potential energy from the potential energy to kinetic energy impacting us. So, okay, of course, I think this is a very typical hazard, the type of the failures that we have encountered. But I think the 4 numbers of this red box, it will be covered under the case studies. Basically to show you some of all these a little bit more different type of the hazard compared to a conventional of circular or non-circular failure conditions impacting us. It's quite interesting, and it's getting more and more rampant on this type of failures, other than those localized earth slip. I think a lot of all this failure is started off with our geology, the generic or the ground, and being due to the tectonic actions, it caused a lot of heave up of our land and create an elevation difference. But of course, I think there are other geohazards actually causing further aggravated the landslide potentials, like earthquake, they're loosening some of the overburden materials. I think some years back in Malaysia here, in East Malaysia, the Mount Kinabalu have a very serious earthquake and really shaken out some of all this overburden very loose. Any rainfall comes, they become a debris flow and quite a very impactful kind of landslide happening. And of course, I think the structural geology also can constitute a lot of these features for instability due to discontinuities, mostly discontinuity causing the instability of this particular weak plane, okay? And this kind of discontinuity also will be inherited to a weathering process to a earth from rock slope, jointed rock slope to this soil slope. Weathering, this 3 type of weathering is very common and causing a lot of overburden, loose material, creating a material for a landslide. Okay, you can see from this is mostly in the East Malaysia, and the level of tectonic actions can really squeeze the material to any form of condition which is adversely impact to have a landslide to that. So of course, I think the other type of the problem actually is a boulder. Okay, a solid boulder is also another form of impact to this landslide. I think without a waters, and I think our landslide will be much reduced. But certainly, water is a well-known mediums other than weakening the soil, and they are also form of transporting medias to bring forward the landslide mass. And I think this is on a bigger scale of the meteorological effect, the monsoon seasons. But now, of course, I think we have a lot more intense rainfall. The climate change altered this sort of a natural frequency of recurrence twice yearly. The monsoon actually now getting more what they call disorder. So we have a lot of extreme rainfall. And obviously, I think the extreme climate change actually does have a very serious impact. It's either very wet or it's not. If not, then very dry. This overly wet or dry condition actually also can cause some interesting features to our soil, and that pose some failures. Later on, I will try to share with you. So today, I think I try to share with you, I think at least about 6 case studies or some from here. One is started off with a very small movement, very slow movement, kind of creep stability. And the other one is some of this material-related swellable joint rock slope, weather rock slope. And the other more impactful actually is the boulder or rock fall. And debris flow is quite common. But this particular debris flow I show you actually is excavated induced the debris flow. And I want to share with you some of the weather conditions, soil and with relic joint, how actually affect the stabilities in the soil slope. And some of the shrinkage potential can also cause problem for the internal erosions. Okay, this is one of the site in Mount Kinabalu, East Malaysia, Sabah, and you can see there's a boulder, displaced boulder moving downward. Means that these are material coming out from the hilltops. Very general, very gentle gradient, 10 degree also can have a creep movement. This is also because partly Mount Kinabalu in the past there's a ice age time. There's an ice cap there, so there's a lot of this colluvium or debris deposited on the foothill, and the drainage system also natural drainage system cutting the ground I want to show you this drainage pattern forming a lot of all these steep slope valley, and that will induce the failure. It's another natural kind of excavations process, and with the high groundwater. So in this case, I think we are investigating a route. We always constantly with the distress. So we monitor the movement at a certain very shallow steep plan that being detected by the inclinometers, and it's creeping all the times. It's actually everyday events. 1.2 kilometer of this paved road. In the past, this site actually has been also have a parallel project running with this micro power, this what they call mini hydro, and not even have a chance to commission. I think the system all break down. The pipeline is parting, crackings, and also the powerhouse also distressed badly due to the massive creeping movement. So this is the monitoring of the inclinometer to show every day, every week. He's talking about 20 to 30 millimeter movement. That's why any installation on the or over this ground, probably you just need a few years. You are move to another property lots already. So this is a creeping movement. It's not a drastic collapse, but it moved very slowly. And the second case, basically, this is also in East Malaysia, in Sarawak. Is a cut slope to accommodate the water tank. Material is very swallowable. Once you excavated, there's a stress relief with the weather. It absorbs a lot of water, causing a lot of distress to the structures before you even able to cover up the slope. This is the geological condition at the site. So you can see once they remove substantial amount of overburden, the stress relief really cause problem here, and all the drain all cracks up. So I think I will skip this. Basically, just to give you a visual, what they call visual expression should be good enough to illustrate this case. This is a boulder, very big boulder, 2,400 ton boulder rolling out from the hilltop, coming down, and you can see the boulder, one detached from the hilltop, is rolling all the way down, destroying any structures along his path. This is a quarters area, very difficult to remove the squatters. I believe in Hong Kong also in the earlier they have the same problems. And I think I want to highlight here, most of all these granitic boulder, these are diorite. When they have an exposure of the soil and the weathered material under the change of moisture content. And I think I want to highlight here, most of all these are diorite. They have of the wet material around the boulder, and when rain comes, you start to get into this gap and erode. Slowly, the material being washed away, become an isolated core string. One string boulders left on the slope. So after a period of time, this boulder, the supporting ground was with a gap there due to the shrinkage, exposure to the sunlight, and it become an easy path for the water erosion happen. Once substantially removed, then the boulder will be left with a very limited point contact, the crushing of the lower boulder with the big boulder on top. So it's a bearing failures. Up to a certain point, it cannot sustain, it will start to move and roll. So we are actually put the developer to stabilize all this move at the spot due to the very dangerous conditions. Once you have any mishap, this boulder will roll down. So we are putting back the support with some concrete and also buttress to stabilize it. Boulder is very naughty fellow, because you let it gain energy, he will really very notorious. So this is one of the what they call movie, okay, short clip of the boulder. You can see it smash on the car and causing casualty. And this is happened in India recently, viral in the website, the internet now. So you can see boulder is not a very easy problem to deal with now. So okay, I think just want to highlight the consequences of this boulder impact. And the other one is a rain-induced debris flow. This is also happened in one of the. I will just fast forward because the time limited. Happened some near a dam site, and the debris flow actually causing very devastating damage to the surrounding. But fortunately, I think the dam is very much well intact. You can see the debris. Once it bursts, the water running down with the debris coming down very seriously impacting the side, our hillside. Okay. Very high mobility. I think Hong Kong have shown some of very serious case of this. So I think I will stop this. Here you can see the running down of this what they call debris. Really is like tsunami. Okay. And this is an induced debris flow due to the excavation of the mine pit. You can see the flowing of these very viscous materials coming down from the what they call landslide. It's really like a flow types of the materials. You can see when it start to fail, it's really like one of the very famous Norway quick clay. Okay, the material just flow with the water, the seawater. I mean, the seepage will just go with the material and very soft and flowable. Okay. So actually, some minor casualty, like just a person got injured. And then another bigger scale is this is in Perak, 1993. A mining site near to the seaside collapsed, become a lagoon. The mining pit become a lagoon eventually next to the coastal area. And I think I want to highlight here, this is the soil slope failure. Before the soil slope fail, actually you can see there's what they call a relic joint. This relic joint basically is a form of previous discontinuity from the weather rocks. So very difficult to detect this sort of relic joint, but it does exist. You cannot rule it out. But then, having said so, you also not able to detect it until it's really show up. Before it crumble, really you can see all this pattern of the grass growing. Have a certain type of strip showing the continuity, repetitive persistency of the relic joint is nothing different from the rock joint. Okay. So it can cause perennial failure or wedge failures. So basically, this is possible things. And I highlighted the boulder. When you have exposed it, the shrinkage, you can cause a lot of gap. And I think I want to highlight here, any shotcretes cover the high slope. With the moisture of the soil depleting, they will form a gap. That's why I think I want to highlight when there's a gap there, the phase capacity of the soil nail may have to be reviewed. It may not be having what you have think in your design. So basically, this is just one illustration. When you have very high phase capacity, you get a high factor of safety, but there is a gap there. You will not be able to mobilize the phase capacity of the structural shotcrete. So the what they call the force diagram will be this blue line, and you will get a lower factor of safety. So it has to be carefully looked into. I think I will just what they call skip this and want to go to the final one because these are all well covered by the earlier speakers. On the what they call this early warning system, actually are we able to have some sensible early warning system? That actually depends on the condition of the slope failures, the type of the slope failure and also the distance of it. So generally, I want to highlight here at about 4 kilometers by brisk walking per hour. So you can see quite a substantial type of the failure. The rate of failure, the movement actually is still well below our walking speed. So except only those rockfall debris that we are not able to capture in time. So the rest of the things I think can be done so long as there's a distance away from us. Okay, I think very last one I would like to highlight on our practice here. There's a factor of safety requirement for treated and untreated slope. And for the treated slope, we actually ask for factor safety 1.5. For the untreated slope, we ask for factor 1.3. But here there will be some interesting part of the calculations because when you reinforce a soil slope, the resistance actually contribute by soil and the reinforcement. So here the calculation, if you ask for 1.3, assuming a certain configuration of the slope give us a driving force of 100 units, we need to have a resistance 130 in order to get a factor safety 1.3. But this resistance can come from soil and come from reinforcement. But when you come to a treated slope, assuming that because our soil can only give me 129, so factor 30 not enough to give it 1.3. So I have to put reinforcement. Once you put reinforcement, the requirement asks for 1.5. So it means that we are actually already reinforcers have to reinforce the slope with higher factor safety. These are the two different cases that for comparison. So I will leave the notes for the audience to have a thought about that. So it's important for us to rectify if there's a chance, room for rectification or making good of this requirement, then we should make an effort, because it costs a lot of money and logical in the design process that we have to make it in the right perspective. So I think I will come to my conclusion. Just now I highlighted because of the land use that we face a lot of population growth, that our land use become more challenging. And I think particularly I share with some of this case study for a foot of thought of some of the problem I highlighted. Thank you very much.
Thank you, Engineer Liu. So our final presentation for today, actually by the President of Hong Kong Society, and its topic is on probabilistic slope analysis considering hybridization of regional and site-specific data of soil properties. So Dr. Andy Leong is actually an associate professor and associate head at the Department of Civil and Environmental Engineering, the Hong Kong Polytechnic University. He has been serving as president of the Hong Kong Geotechnical Society since June 2022. His research interests include soil structure interaction, reliability of geotechnical and structural systems, probabilistic analysis approaches, and risk assessments. He has received multiple awards on teaching research and not bring university research to the practice. So I'll hand over to Dr. Andy Leong. Thank you.
Thank you very much, Dr. Gui. Let me quickly share the screen. Right, so the topic of my talk today is probabilistic slope analysis considering hybridization of regional and site-specific data. I'm going to define these terms very shortly. Right, so let me start with something that we probably all know already. So this pie chart on the bottom left came from a survey in the UK some 20 years ago. And in that survey, the project managers were asked a question about their projects. When they have a trouble in their projects, what was the usual cause of the problem? And then around 22% of those respondents said that the unknown or uncertainty in the soil boundaries caused the problem. Some 20% said that the soil properties, or the fact that we did not know exactly what the soil properties are, caused the trouble. So you can see that when these two components are added together, roughly 40% of the issue in geotechnical projects arise from soil boundaries, soil properties, or the unknowns surrounding these components. In fact, when it comes to the calculation or detailed design process, they usually are not the main cause of the issue. So if we come back to the idea, well, if we come back to the topic of slope engineering, so I have made a conceptual diagram on the bottom right. So the blue one is for a hypothetical slope 1, which might have a small estimate of factor of safety, maybe roughly around 1.5 or so. But that's only the best estimate of the factor of safety. Because of the unknowns in the projects, we always have some sort of uncertainty in the estimates of the factor of safety. And in red is a different slope 2, which you might have a bigger estimate or bigger best estimate of the factor of safety, almost around 2. But it's really not just about the best estimate. It's also how uncertain we are with our estimates. So if slope 1, there might be a lower uncertainty regarding the soil properties, groundwater conditions, and so on, then the uncertainty in the factor of safety is relatively narrow. On the other hand, slope 2, it might have a higher best estimates of factor of safety, but it might be associated in a higher uncertainty, and therefore it gives you a wider distribution. In that case, we can also define the probability by the area of these curves which lie in the zone where the factor of safety is smaller than 1. So in that sense, actually slope 2 can have a higher probability of failing, even though our deterministic best estimate factor of safety could be quite high. So I hope that gives you a taste of why it is important to try and understand or quantify uncertainty and how it affects our slope engineering estimates. So I have a quote which is somewhat related to geotechnical engineering. If we want to define or quantify uncertainty, obviously we're going to need data. So these two quotes, I can give you 5 seconds to think about where they came from, but I think this is very much related to our profession. We need good data and we need lots of them. So this quote is actually not from the Kiyosakis or Casagrandis of our profession, it's from Sherlock Holmes. But then again, I think it's very relevant to what we are doing in our profession. We need good data. And I'm going to use the next 11 minutes or so to talk about how the use of data may affect slope reliability assessments. So in the beginning of today's event, engineer Roy Hong of the Geotechnical Engineering Office of Hong Kong, he mentioned this G-Info system where our government has combined lots and lots of investigation reports and testing reports and then compile them very nicely and put it into this electronic platform. And then for those testing data, most of them are from the high quality samples obtained from the field, either by the core samples or the block samples, and they're very carefully transported to the lab for the high quality triaxial testing in order to obtain the shear strength parameters of the soil materials in Hong Kong. So in this regard, our authorities are very careful and very good at controlling and making sure that our profession follows good standards in testing of our soils. So over the years, we have compiled a good number of data for the different types of soils in Hong Kong. So this one, COLL stands for colluvium, and this one obviously is fill. CDG is completely decomposed granite. CDV is completely decomposed volcanics. All of these are very typical soil types that we see in Hong Kong. And this number here denotes the number of multi-stage consolidated undrained triaxial compression test results. So for example, taking the red one, CDG as an example, we've got over 700 data points, and each data point comes from multi-stage triaxial test results. So we have a reasonably, well, very good record or database of the material behavior. And just a quick note that most of these tests involve confined pressure smaller than 200 kPa, because those are the predominant stress levels that we face for the slopes that we usually encounter in Hong Kong. So obviously, if you've got so much data, you can plot the probability distribution of the cohesion and friction angle values for each soil type, which is precisely what we've done here. The cohesion and the friction angle based on hundreds of data points from each soil type, we're able to quantify the variability of the material using the probability distribution functions. But then these PDFs, they're really for the region or for the entire city of Hong Kong. So Hong Kong is a small city, but then soils can have their properties varying at different parts of our small city. And these probability distribution, they only show the distribution of properties for the soil across the entire city of Hong Kong. But then you may have a question in your mind. So even though we have the PDF for entire Hong Kong, are they really applicable for my own site? My own site could be a very small spot in the context of the entire city. So those PDFs, are they actually applicable or useful for my own project? So we need to think about this question very carefully. So in a project-specific context, should we adopt or use design parameters based on our regional knowledge, which is this one? Or should we get the parameters based on only the data from my own sites, which, as we all know, could be often limited? So if we use number two, the problem is we don't have a lot of data at the site. If we use number one, the problem is that a regional database may not be applicable to my own specific site. So what we're trying to do here is trying to combine the benefits of both worlds. We try to hybridize or combine our knowledge from our particular site to what we already know in a regional based context. So the question becomes, how can we find a rational way to perform this sort of hybridization or combination of knowledge? In fact, a few years ago, in 2019, there's a very interesting, very good paper published by Professor Cheng from Taiwan, Professor Fun from Singapore, which talks about this idea of hybridizing information. So the concept is that you might have a generic PDF covering the entire region, and you might have a site-specific PDF for your own particular site, and we can try to combine. So on the left-hand side, in this case, if you have very limited site-specific information, the hybrid is going to be very close to the generic. So the gray dashed line is almost overlapping with the black solid line if you have very few data. But if you have lots and lots of sites data, then the data will demonstrate some sort of features that only apply to your own site. And if you combine this site-specific with the generic, then your hybrid, which is the gray dashed line, is going to shift towards your site-specific characteristics. So this idea is really trying to combine logically our background knowledge, the regional, with our new data, the site-specific information. So what we're going to do is following this similar logic, although not exactly the same mathematical framework, but then it's a similar logic. So coming back to the case of Hong Kong, I said that for the soil called a completely decomposed granite, we have over 700 test specimens or testing data points across the entire Hong Kong from more than 200 sites. And if we have a specific new site around these spots, we can try to hybridize the new information with the regional data. And I'm not going to go into the specific details of the mathematical framework. We call this the, well, it's not that we call it. This is called the hierarchical Bayesian model. Well, like I said for several times already, the main idea is to combine information from the sites with our background regional knowledge. And in the process, we're going to identify and quantify the variations of our shear strength parameters within each site and also across the different sites in different parts of Hong Kong using this sort of mathematical framework. And then there's a model training process. There's an also combination or hybridization process. I'm not going to go too much into the details with the consideration of the time. So we applied this sort of idea into a landslide case. What landslide itself happened some 26 years ago at a place at a location called the Ching Cheng Road in Hong Kong. The slope failed after intense rainfall due to a typhoon. And then in the geotechnical investigation, we obtained 25 sets of site-specific Traxel test data, and we know the groundwater level reasonably well from the investigation of the landslide. So basically, I believe that most of the audience you're familiar with the program Slope W. So in the Slope W program, you can specify the slip surface in your slope analysis. And in fact, there's a functionality in Slope W where you can click Monte Carlo simulation to give you probabilistic analysis, which applies to a one of the slip surface. But then from the version of Slope W that I use, that Monte Carlo simulation will only apply to one slip surface. And we all know that slope can fail in a number of potential slip surfaces. So what we did in this case is that we defined some 10 slip surfaces, and then we run the Monte Carlo simulation using the Slope W program, and we compile all the results from those 10 times 2000 Monte Carlo simulations in order to obtain the probability of failure for this slope in a systematic sense. So this is what the these are our probabilistic slope analysis results. Basically, there are two lines: the probability distribution of the factor of safety. Obviously, if the FOS is smaller than 1, that indicates that the slope is going to fail. And using those Monte Carlo simulations, if we only use the regional background knowledge of the CDG soil, we get this distribution of FOS with a certain probability of failure close to 0.8. But if we hybridize and combine the 25 site-specific data points, we obtain a different PDF for the factor of safety that indicates an even higher probability of failure. The diagrams at the bottom just to show you, how when we increase the number of site data that we incorporate into the hybridization, how our estimates, the black one, are going to shift away from the regional estimates that we show in here. So in the interest of time, I have to quickly wrap up. This is the second last slide. The idea is that sometimes we feel that at a particular site, you can actually never know the real distribution of C fine. But then we can try to conduct these hypothetical thought experiments and saying that assume that the PDF of C fine parameters are completely known. If we can specify the probability distributions of shear strength parameters, then we know the true failure probability of that slope, which we indicate using these horizontal lines, the gray lines, gray dashed lines. So here, just to show that if we incorporate site data into our hybridization approach, our estimates of the probability of failure is going to gradually migrate towards the quote-unquote true probability of failure. So in this case, we see that if we can have 20 to 25 site data, put it into our hybridization approach, we will be able to get estimates very, very close to the real probability of failure based on our specified or assigned PDF of the shear strength parameters. So, well, in the interest of time, I really have to close the presentation here. Just quickly acknowledge the funding agency, the Research Grants Council of Hong Kong, and this study is a collaboration between my university and the Geotechnical Engineering Office, and all these engineers, postdoctoral fellows, they contribute tremendously to the study. So with that, I would like to wrap up my presentation. Thank you.
Thank you, Dr. Andy Leong. So I think we will now take a break and then we will resume back at 12:20 for the panel discussion.
Hello, can you hear me? Testing. Okay. So I would like to read out the first questions. This question will be to Dr. Sukri. So, but other panelists are welcome to answer. They are two government agencies looking after slope instability or risk issue, which are JKR and JMG. May we know the boundary of the responsibility of coverage between these two agencies?
Right. Thank you for that question. Uh, okay, you can see that the between JMG and JKR is doing a separate work actually. JKR is doing the linear based plans, however JMG is doing the area plan. I mean the details have been explained also with the Dr. Lau actually. So on Jacob part, we are not only doing the linear base, but also we are doing preventive and also preparing and also implementing any of the preventing and also mitigation for those potential landslide areas. Okay.
Hello. Okay. Thanks, Dr. Sukri. We go for the next questions. Also for Dr. Sukri. Okay. Could you please update us on the progress of the slope master plan aimed at upgrading the JKR slope division to a national slope agency similar to GEO Hong Kong? The objective of the upgrade was to provide support to the 149 local authority in Malaysia.
Okay. I think this question also can be answered by engineer. No, Liu. Because we are in the same committee for Master National Plan. As I mentioned before, 94% of the key elements has been achieved. However, in the bigger picture, this question actually there be some similarity between CKC and also this CED in Hong Kong. However, our parts actually a bit small from the CED actually. So I'm thinking that we should have a bigger mandate so that we can be as the same level or that the CED is doing at the moment actually. So of course the 149 local authorities will be benefited from the enhancement from this national master plan.
Actually, I think the government have taken a step to slowly materialize it. And of course, there are different agencies taking part of the different aspect of this geohazard management. And quite clearly, obviously, the JMG will have a lot of media exposures. When the incidents happen, mostly the media will ask for geologist input, and whereby I think the engineer is the one that behind to make good of all these damages and follow up reporting actually is relatively less. Only happened to be first instance when the issue come to the public medias. So that's what give a little bit wrong representations on the contributions of this landslide management. Obviously, I think to have a centralized agency will need to take a little bit more effort in coordinating among the different agencies. So I think this is more towards the government side to pushing it, and as a publics or even private practice, we would really like to see the merging of coordinations when come to all this sort of landslide risk management, so that we have very clear directions on the guideline, and also those are design code standard to follow lah. Maybe it will be also good to hear some Hong Kong practice that we can follow or considers.
Oh, actually, I'm wondering if Roy from GO would like to add a bit of insights from the Hong Kong government's side.
Hello, Andy, I'm here. I'm here. See if this is the way I understand the question. The question is about how the governmental action can be better coordinated in addressing the slope or the landslide risk, isn't it? Is it?
Yes.
Okay.
Yes.
Put it this way. First of all, I think the scale, the problem of scale in Hong Kong is not comparable to that in Malaysia, right? Malaysia is a state with a much larger territory, right? But put it this way, in Hong Kong, even though we are a city with a population of about 700 million, okay, 7 million, right? Whatever in Hong Kong, we also have a system of how the government agencies coordinate among ourselves in managing the landslide risk. Okay, my view is that whatever way within the government, there's a division of responsibility. There's always a collaboration and a common goal to do the best to address the landslide risk issue. Okay, in Hong Kong, put it this way, we, the Geotechnical Engineering Office, actually is taking the role of overseeing all the landslide risk management issues. I would say that we are overseeing because we are not the only party to do the job. Actually, in fact, in Hong Kong, there are different government departments responsible for the different area of slope landslide related actions. I would say that. For example, for the daily maintenance, actually, we have assigned all the government slope to different government departments to do the slope maintenance works on their own. Okay, and we allocated resources to each of them. But having said that, we, the Geotechnical Engineering Office in Hong Kong, actually is taking a role to coordinate, to set a good standard so that all the guys are doing the same job to the required standard. And I would say that we are taking a role to make the system better, if not perfect. That is, in case there are separate parties that are doing the things in the same region, right? We try to coordinate it to do it in a resource efficient manner, put it this way. So this is, in some way, this is the way that we want to make the job better. That is to make the coordination better, and then to set a good standard so all the work, all the people can do the work. All the people do the work in the way they do, but more efficiency and in a coordinated manner.
Yeah, thank you very much, Roy. Actually, I have a follow-up question to our Malaysian counterparts. Understand that in the case of Hong Kong, when we are setting new standards or pushing new boundaries in slope engineering, the government is very proactive in engaging also the universities, like new research be it Hong Kong U, Poly U, or HKUST, CTU. I'm just wondering if the Malaysian governments or authorities in all these committees, do they actively engage the researchers or university professors in giving advice to the new policies?
I think everywhere else in the world actually we appreciate on the academician actually. Same goes as Malaysia. I mean, if any new guidelines or manuals or any technical notes, we also be inviting most of the researchers in local university or in the private university. In fact, we are also inviting from the overseas actually. We are very welcoming on the expert or the academician to improve our manuals or any of the technical document that being used at the moment.
Okay, thanks. So I would like to go for the next questions. It's also about JKR. So is the appointment of concessionaire air for the slope study by JKR gone through open tender? Then the next, can you share the information to tender the job?
Okay, to be frank, actually, we have this concessionaire contracts. However, this concessionaire is directly appointed from the Ministry of Finance. So all the implementation, all these procedure contracts will be discussed in the high level. So under the purview of Ministry of Finance. So the second question is how are you going to tender the work actually? This one is, I think, maybe the question from the subcontractor or the consultant. So as I mentioned before, under this concessionaire, all the works were given under this company. So the subcontractor, the consultant need to see this concessionaire. Okay. I think most of our consultant in Malaysia knew about this contract actually. Okay. I'm talking particularly on the road maintenance by federal and states. But we have another one is maintaining design for the building slopes. But this building slope is will be directly under the slope engineering department. Okay.
Thanks, Dr. Sukri. Next questions. Is JKR responsible for slope failure in Malaysia? If not, then who shall be responsible? Another questions. Any target in terms of number to reduce loss of life in slope failure in Malaysia?
I mean, we have I mean, from this presentation, I mean, we have no the triggering and contributing factor is you have so many aspects actually. So actually is how you call the factor is too many. I mean, JKR is not the one who contributing the landslide actually. So many things. You got this rainfall, you got some vegetation, geotechnical assessments, so on. So we have to look on the bigger picture actually. So what is the contributing factor or triggering factor actually? And so the slope also was not meant for the JKR only. You have slope belongs to the private sector, individual, or the local community, local authority, highways, so on. Okay. Next question. can't remember.
Any view from the other panelists?
Or maybe we have also from the Petronas, so we are also looking on their slope also.
So maybe I like to also reiterate what Dr. Shukri mentioned. The variables are many, and the influences of external factors compounds to that complexity. So people usually say, okay, after the rain, slope failures happen. Well, sometimes that's not the case, right? So that's why for Petronas, we are exploring machine learning lah. So hopefully the machine can tell us something. Thank you.
Have anything?
Yeah, I think one of the very important aspect after the slope being formed, the following up maintenance and inspection is very important. Particular some of all these drainage and with the extreme climates conditions, we can see a very devastating and extensive damage due to debris flow. Okay, so I think the drainage is one of the very important aspect in the slope engineering. But then for a normal residence or whatever, when you have properties behind got a slope, actually they have expectations the marginalis will have to take over the inspection and maintenance of this slope lah. So that's why I think you put a lot of burdens to the marginalis, and really seriously marginalis should also beef up the technical teams to maybe you can have a special force collectively handling these matters and provide awareness from those population at risk so that they know what they will be looking for their own good safety protections. Then regularly reported and demand inspection to safeguard themselves. But of course, this involves a lot of time and resources. So whether marginalis will have the budget for that or not, you really have to seriously think. But safety can never be compromised. Once incidents happen, there will be a lot of all these morals issues to entangling them. Thanks.
Okay, thanks, Engineer Liu. Any view from Dr. Loh? Anything you want to add, Dr. Loh?
Okay, maybe I can add some of my thoughts here. As what the question asks, is the responsibility, is JKR responsible for all the landslide or not? Apparently, as what Dr. Ahmad Shukri mentioned, you see, in Malaysia, a little bit different from Hong Kong. We have state governments and we have federal governments, right? Now you look at the engineering branch or engineering slope divisions, apparently is fall under the federal governments, right? So we do have another level of government, which is state governments. So when state governments, we have these local authorities who are actually taking care of the housing areas and all these development areas, right? As for public works department, are mainly concentrated along all the roads, all the government roads, all right? And then we have area like, for example, I'm taking care for Resort World, right? The access road, which is a private road. They actually have to do their parts, they actually engage us to do some risk and hazard assessment along the access road. They actually implementing real-time early warning systems along the roads, So these are the things. So different parties, I think you have a role to play. Even let's say you purchase a house where you have actually seated on slopes also. As a house owner, you must play a role. That means you must do your regular inspections on the slopes to ensure that there is no, for example, tension cracks. There is no broken drains, and these are the role everybody have to play when it comes to slopes issue. That is my view. Thank you.
Thanks, Dr. Loh. So I go for next questions, also for Dr. Shukri. Could you please share with us on the effectiveness of the earlier warning system implemented in the highway?
This question, thank you so much. I think this is the fifth question. Question to the JK. Actually, it go back to what been mentioned by Dr. Low. Actually, JK is only concentrating on the federal road and also state road. It depends to the which level. But however, highways also, you got other bodies who are taking care of. For example, the North-South Expressway was under the plus actually. In relation in that actually, of course, in the federal or the state road, we have installing some EWS, but the effectiveness is depending on the numbers and also how do you monitor. But I can see that the presentation from Dr. Low actually he has mentioned that from his past experience, the effectiveness of EWS. Maybe he can explain a little bit more.
Yeah, all right. Okay. As for early warning system, as I mentioned just now in my presentation, we have actually about 85 numbers of rain gauges along Plus Highway, right? And then for Genting Highland Access Road, we have about 8 rain gauges. Now, we actually having a threshold for all the rain gauges, right? Now, this threshold, as I said, we developed the threshold from one of the debris flow incidents took place back in 1993, all right? That is actually at the Genting Sempah debris flow, right? That killed, I think, about 19 lives. From that debris flow incidents, I think we actually try to map out all the landslides in the 5-kilometer radius. They have, I think, about that incidents actually caused about, I think, about more than 50 to 100 landslides along that 5-kilometer radius. So based on that failures, right, the type of failures, and then the mode of failures, and then the size of failures, all these actually have been mapped, and then we got the rainfall records from the meteorology departments, and then we try to actually figure out what is the threshold, right? So the threshold actually, as I said, it works very well along on this Genting Highland access road. As I said, back in 2021, before the landslide, 200 landslide took place, all my 8 rain gauges actually triggered, right? And then immediately after trigger for a couple of hours, landslides start to take place one by one, right? It start to come down one by one, and subsequently, and because you have early warning, there's no casualty, right? There's no casualties, and then the civilian teams and the maintenance teams of Resort World, they actually stand by all the machineries at the mid hill, right? To stand by. This is the function of early warning system, right? So that they can actually immediately, they can, if anything actually come down, they can actually clear the incident site, I think within maybe like 1-2 hours, because they cannot afford to close the road, right? Because we have a casino at the top of the hill, right? So they are very effective in terms of landslide management, all right? So with that rainfall threshold that we've given to Genting, that works. That's why we, along this Plus Highway also, we have actually installed about, if I'm not mistaken, it's about 85, right? In the range of 85 to 100 rain gauges, right? And currently it's still, we are still monitoring it, right? In some area we have even real-time piezometers, right? I'm actually monitor the flood as well at some points of the highway as well, right? Putting up some real-time monitoring system. Yeah. It works, actually it works. That's my comment.
Thanks. Hello, can you hear me? Okay, sorry for the some technical issue. Pertaining to this early warning system, would like that whether the panelists from Hong Kong would like to share your experience on this. I believe that you all are more advanced compared to Malaysia on this.
Oh, okay. So looks like there's an issue with the connection of the microphone. So I'll just use the laptop. Well, actually, I'm afraid I'm have to refer or this question to Roy again. But I understand that in Hong Kong, we also have a very good number of rain gauges across the city. And in the past, there have been some studies on the correlation between the rainfall intensity and the number of landslides that may occur. And then we also have a very extensive and well-established landslide warning or early warning system that has been implemented for many, many years already. But then I'm sure that Roy will be the person to supplement on this particular topic.
Okay, Andy. Well, I'm happy to take this question as well. But put it this way, let me just briefly share what Hong Kong has been doing, right? So Andy, you're aware that we have a long history of rain gauge to monitor the rainfall and trying to correlate what we have about the rainfall data, correlate rainfall data with the landslide. Okay. In fact, we have many rain gauges. I don't have the exact number because sometimes we will install more rain gauges. I understand that there are two different parties in Hong Kong that is doing the rainfall monitoring. First of all, is our Hong Kong Observatory, and also we, the Geotechnical Engineering Office, also have our own set of rain gauge, and we combine the two sets to have a quite comprehensive rainfall data. Actually, we have a real-time rainfall monitoring data around the clock, and then so over the years, we have been doing research to correlate the rainfall data about the landslide risk. But put it this way, I believe rainfall is an important contributor to landslide, but it's not the only one. Okay, so in fact, for landslide to happen, there are many different factors, maybe as more controlling as rainfall. For example, the landslide susceptibility, where it is, ground condition, etc. So work on this area will never stop. Okay. So the second thing is about the landslide warning system, isn't it? Andy, you're right that we have such in Hong. For those who live in Hong Kong, you should be always aware of those weather-related warning system, right? Because you should be always stay alert with whether it's those rainfall warning system, typhoon, and the landslide is also one of it. Actually, we have been introducing this landslide warning system for years, and in recent years, we also have another indicator to our alert public is we introduce a so-called landslide potential index, okay, which is trying to quantify the likelihood of the likelihood of landslide that will happen during rainstorm. Okay. So, Andy, so what was your question? It is how we work on the landslide warning system, or what do you like to know more?
Oh, I think it's mostly about the landslide warning system, its implementation, or
Okay.
how you interact with Hong Kong Observatory to issue those warnings.
So just briefly talk about how it operates. Okay. The one who issued the warning system is our Hong Kong Observatory. Okay, but they seek our technical advice on how we relate the rainfall with the landslide risk. Okay, so I think the correlation between it depends on our previous study, but I think always is the most important is the real-time monitor of the rainfall using the rain gauge. Okay, so actually, when there is a rainstorm that we foresee it will be coming, so this geotechnical engineering office we will alert ourselves. Okay, so we will start looking at our real-time monitoring system round the clock, and then always just to compare what the real-time rainfall is against our historical correlation. And then we have some internal criteria to say that, well, if that is the rainfall, the accumulative rainfall that is about to reach a certain criteria, we'll think about whether we should issue the landscape warning or not. But there's always a judgment here in our top management, because issuing a warning system like that will have a societal impact to all the people working around, isn't it? So we were looking primarily on the rainfall data, but we will have our judgment. And when we think that is the time we use the warning system, we will refer our recommendation to the Hong Kong Observatory, and then they will just issue it. And then it will be announced all the way to all the Hong Kong citizens through all the media means they have. So this is the way we operate our landscape warning system. So once we hold the system during the rainstorm, okay, the system will continue. So when will the warning be eased? Okay, that is again we'll look at it scientifically at the rainfall data. Okay, sometimes when the rainstorm is ending or is about to end, okay, there's no rain anymore, because you see that when it's a typhoon in Hong Kong, we'll be hit by typhoon. Okay, the typhoon at its peak hour, it will be hitting Hong Kong for a duration of about 10 to 20 hours, 10 to 12 hours, say, okay. So when the typhoon is nearing the end, there's no more rain, okay? But as our landscape warning will still be there for maybe a couple of hours, because actually landslide will come after the rain based on our experience. So that is why we always make our judgment whether it's a host the landslide warning or not only about the real-time rainfall, but taking into account all our experience about what is the likelihood of the landslide will happen.
Right. Yeah, thank you very much, Roy. That's a very comprehensive answer. Well, in the interest of time, I would like to direct the next question to Johan. Right, so it's about the machine learning. So there's a question from the online audience. First, a compliment. It's a very nice and in-depth presentation on leveraging machine learning for geohazard impact management. Based on the presentation, technology, data acquisition, and site performer database has been included in the machine learning program for assessment. The question is, does specific selected slope analysis are being performed to calibrate with the machine learning tool program by Petronas? If yes, can you share some of the brief outcome from that calibration exercise?
Okay. Okay. First of all, thank you for the question.
So
Let me just get it correct.
whether we use
Conventional finite element or slope stability analysis to calibrate our machine learning. Okay, so far, no. What we've done to calibrate our machine learning to derive our risk score and probability of failure is via validation of our geologists who goes to site, who from their judgment that location is high or low or medium risk, and that is calibrated against our machine learning findings. Okay, so how we look at doing finite element analysis or stability analysis is when we want to do specific repairs to any particular location. So that is a different requirement for natural slopes and man-made slopes. So for us, it's mainly natural slopes. So because we are a remote location and we are inaccessible at some of the time, So to repair those locations might be difficult, right? So not necessarily so all location we do slope stability assessments, and we try to also use our experiences for some of these locations to do that lah. So to answer you directly, no, we are not currently collaborating with finite element or slope stability analysis for our machine learning. Thank you.
Maybe I can add on something on that, Tuan Haji.
Okay.
Okay, because you see, when you talk about analysis on hazards and risk, as I said, machine learning is part of one of the type of more advanced statistical tools, right? And for calibration of all these machine learnings or statistical tools, apparently you need to have data. As I said, you need to have sufficient data sets. Data sets in the sense that for you to do the calibration, you must have failure records, right? That is the best data for calibration. It's not so much on running finite elements. It's not so much on running stability analysis to calibrate the data, right? But it's more on the failure records. For example, you have a road, right? When you want to use machine learning or any neural network, for example, right, systems, you need to have sufficient failure records, right? Then only you can actually have a very effective analysis tools on that.
Now testing. Thanks, Dr. Lau.
Yeah.
So we go for the last question for today's forum. Okay, this is for Prof. Wong. How do the newly developed rock slopes design curve in Prof. Wong's paper compare with the alternative GHB severity chart developed by Lee, Marify, and Lyman, in which modification to the GHB equation were presented for steep and gentle slope? It would be much appreciated if Prof. Wong could share his paper.
Okay, thank you very much for the question. So I believe that you are referring to a previous paper of Dr. Lee. So I think, well, it is quite a few years ago that I did this work. So I have to recall my memory a little bit on this. So actually, I think in our paper, we only did the limit equilibrium analysis, okay? So we make this Taylor series expansion of the GHB criteria, and then using it to establish these charts for the rock slope design. Whereas in the paper, previous paper of Lee, you mentioned, I believe they did both limit analysis. So so basically, I think they did both lower and upper bound analysis, and then they used the HGB criteria in both lower and upper bound analysis and establish the charts. And I think if it's the same, the HGB criteria being used, I think the chart results from the upper and lower bounds provides fairly good estimates, which are comparable to the charts in our paper, okay? So I think it's quite, the error range bracket by the upper and lower bound is quite narrow, I believe. I think maybe a few percent, I guess. So I would say their charts is in good comparison, okay? Well comparable to our charts. I think the problem is when you are using the equivalent MC criteria. So there are problems using the EMC stress parameters in the limit equilibrium analysis, okay? So I guess the problem is in the accurate and reliable estimation of the minor principal stress. So I guess in their paper, the paper of Lee, I think they proposed some empirical equations to correct the minor principal stress for the steep and gentle slopes, and to produce the equivalent MC parameters, which are subsequently used in the limit equipment analysis. And I believe that this kind of modification has produced the better results, okay, on the factor of safety. So I guess this perhaps is the answer that you want. Thank you.
Thanks, Prof. Wong. So I believe the forum come to the end. I would like to thank all the panelists from Malaysia and also from